The National Academies is committed to fostering a professional, respectful, and inclusive environment where all can participate fully in a harassment-free and discrimination-free atmosphere. And we look to each and every one of you to be a partner in this commitment by helping us to maintain a professional and cordial environment. I'd also like to ask that each time that you turn your microphone on, or if you're online, well, turn your microphone on, that you introduce yourself, just your first name, and that you avoid acronyms. There will be one we'll probably hear quite often, BESR, for the Board of Earth Sciences and Resources. We'd like to try to avoid that. So the Board on Earth Resources, a little background on the National Academies, is a nonprofit, nonpartisan organization that provides independent, objective advice to inform policy with objective scientific findings, spark innovation, and confront challenging issues for the benefit of society. The Board of Earth Sciences and Resources was established in 1988 to provide a focal point for activities related to Earth science policy. And you see here the committee membership. And through its committees, panels, and working groups, the board oversees a wide range of Earth science issues, including the environment, natural hazards, resources, geographic science and geospatial information, data, and education. And I invite you all to look through the agenda booklet for the members' bios. And the Committee on Earth Resources is a standing committee of BESR and is responsible for developing activities of Earth resources and providing a forum for the exchange of information between the Earth sciences community. And again, the committee is chaired by David Spears, who you'll hear from in a little while. The members of this committee are shown here, and I invite you again to look through the agenda booklet for the members' bios. So David, I'll turn it over to you now to introduce our meeting topic.
Thank you, Isabel, and good morning, everyone. Is brines as a resource for critical minerals. And let's just take a second to think about those words, brines as a resource. It wasn't that long ago that brines were primarily thought of as a disposal problem. In 2017, just 7 years ago, under the guidance of this very board and this very committee, the National Academies hosted a workshop that was called Flowback and Produced Waters. And the proceedings of that workshop are available on the Academy's website. And if you read through them, the discussion was primarily, what do we do with all this salty water? At the time, hardly anyone was thinking about the solutes in that water as a resource. So one of the charges to the Committee on Earth Resources, and really to all the committees at the National Academies, is to look ahead. What are the changes we see coming in the Earth resources landscape? And what can we do as a committee to bring together the people who are leading those changes and have a productive conversation about the future? That's what we're doing today. We're looking ahead. We've got leaders in this room, people who are leading the whole science in the area of brines of the future. So as the global energy transition accelerates, geologic brines are an increasingly important resource category, which offers the potential for economic critical mineral recovery with potentially lower environmental impact than conventional extraction methods. Brines are defined as basinal or connate waters with elevated concentrations of primarily sodium and potassium salts, along with other dissolved metals and minerals. Specific mineral resources, of course, depend on the geologic setting of the brine and may include things like lithium, manganese, boron, bromine, phosphates, potassium, magnesium, soda ash, sodium sulfate, and rare earths. Brines can occur as co-produced waters with oil and gas. Brines may be associated with may be independently produced as standalone resources. In this webinar, we will examine domestic mineral resources found in brines. We'll also examine the origin and longevity of the resource, the different mineral extraction technologies, and the potential environmental impacts of developing these resources. Our panelists have compiled a list of recommended references that we will page through quickly here. Page through, there we go. Suggested references. There we go. Suggested references from our speaker. So that's quite a list. You don't need to copy it down. You don't need to read through it now, but if you'd like to refer to it, you can go back to the recording of this meeting and take a screenshot, or take a screenshot right now. So we're going to begin, and our first speaker is Jennifer McIntosh. Jennifer is a professor and university distinguished scholar in the Department of Hydrology and Atmospheric Sciences at the University of Arizona, and she's a joint faculty member in the University of Arizona Geosciences Department. Jennifer, please take it away.
Thank you, David. Margot, will the slides show up on one of these monitors so that I can see them? Or should I step away from the podium? Okay. Great, thank you. Good morning, everyone. Today, I'm going to give an overview on the hydrogeological origin of brines. There are three different types of lithium brines and brines in general. The first is brines that are found in sedimentary basins, which may or may not be associated with hydrocarbons. Brines that are produced with oil and gas are called oil field brines. These brines are low temperature, less than 100 degrees Celsius. The second type are brines that are found in closed basins or salars. They're also low temperature. We sometimes call these brines continental brines. And then the third type is geothermal brines, which are over 100 degrees Celsius. I think it's important to note that in lithium and other critical mineral brines, we often find a mixture of these three different types. So for example, I'll show at the end of my talk, geothermal brines that are inputted to sedimentary basins or closed basins that bring things like lithium. There's evidence of sedimentary basin brines and closed basin brines that circulate through geothermal systems. And there are some locations where you find sedimentary basin brines at the bottom of closed basins as they transition from marine to more terrestrial environments. In my mind, one of the best ways to distinguish between these different types of brines is to look at their stable water isotope composition, because that tells us something about the origin of the water. On the left is a plot of the hydrogen versus the oxygen isotope composition of the waters relative to the global meteoric waterline, where rain or snow precipitation will plot. Brines within sedimentary basins, such as the Appalachian, Williston, Gulf Coast, and Paradox basins, come from the evaporation of seawater in the geological past that forms this hook-like pattern. These high-density saline brines have been diluted along their margins by meteoric recharge. There are some locations that I'll highlight where you actually see meteoric water that's dissolved salt to create a brine. Geothermal brines, on the other hand, often come from meteoric water that has then been modified through high-temperature water rock reaction, which increases the oxygen 18, plotting to the right of the meteoric waterline, such as we see in the Salton Sea system. Closed basin brines, such as in Clayton Valley, may have some input of geothermal waters, but these brines primarily get their salinity from evaporation of groundwater that has a meteoric origin and plots along this evaporation trend. So now I'm going to go into more detail into these three different types of brines and their origin. So starting with sedimentary basins, this is a map of the United States showing the 95th percentile of lithium concentration in these brines. As you can see, the highest lithium concentrations is found in sedimentary basins that have a marine origin. So they have evaporite minerals that are precipitated from seawater and residual brine that came from evaporation of that seawater. As seawater evaporates, salts are left behind, like chloride and bromide, and we'll see lithium. The plot on the left is chloride versus bromide, and in the black line is the evaporation of seawater. These brines in places like the Appalachian Basin are highly evaporated seawater going back hundreds of millions of years ago to the Paleozoic. As seawater evaporated, it precipitated halite and often potash salts, which are found in these basins, and then those residual brines that are highly saline and dense. There is some salt recrystallization enriching these brines in chloride. But again, many of these brines at the margins of these basins have been diluted by meteoric recharge. And again, there are some locations where that brine has been displaced and fresh water has dissolved salts, and we can distinguish those types of brines based on their chloride to bromide ratios. These seawater, evaporated seawater derived brines have been modified through water rock reaction. So compared to evaporation of seawater, we see these brines are highly enriched in calcium and depleted in magnesium, and that's because of diagenetic reactions with carbonate and silicate minerals. At the same time, lithium is highly enriched in these brines relative to the evaporation of seawater. We see the same pattern with potassium. The magnesium to lithium mash ratios in sedimentary brines are variable, although the median is usually greater than 10. Again, if we look at lithium versus chloride to bromide ratios, we can see that the highest lithium in sedimentary basin brines comes from the ones that derive their salinity from evaporation of paleo seawater, where brines that get their salinity from dissolving salt generally have low lithium concentrations. So turning to the second type of brines within closed basins, these brines come from meteoric waters that circulate through mountain blocks or are recharged at the mountain front. They carry solutes like lithium from mineral weathering. And then as these meteoric waters flow through these basins, they react with the sediments. So through dissolving or precipitating minerals, lithium becomes concentrated, as well as through absorption and desorption reactions with clays that can be sources or sinks of lithium. The timescales of circulation of these closed basin brines ranges from hundreds to tens of thousands of years. Extensive evapotranspiration in the center of these closed basins removes water, which is the only outlet, and leaves behind evaporite minerals, salts like lithium, which becomes enriched in the shallow brines that are left behind, and saline lakes. The highest lithium brines in closed basins tend to be in ones that have a salt crust or playas and only ephemeral saline lakes. As groundwater evaporates in these closed basins, a series of evaporite minerals precipitates and the final brine composition changes, depending on that initial groundwater chemistry. So for example, if the groundwater is enriched in carbonate, say from a magmatic CO2 source, then you tend to precipitate magnesium salts, natron, trona, and halite, and the residual brine is enriched in sodium, carbonate, and chloride. This type of brine we find in places like Mono Lake and Cyril's Lake, again, where you have magmatic CO2. If the groundwater was enriched in calcium and sulfate, then you tend to precipitate mirabolite and halite, and the residual brine is enriched in sodium, sulfate, and chloride, like we find in the Great Lake. If the brine was enriched in calcium relative to carbonate and sulfate, you tend to precipitate gypsum and halite, and the residual brine is enriched in sodium, calcium, and chloride, like we find in Clayton Valley. If lithium is present in the inflow waters, either from weathering sources or geothermal inputs, lithium will be enriched in these residual brines because lithium is an incompatible element that does not get precipitated into these evaporite minerals. Obviously, the sequence of chemistry in evaporite minerals is more complicated depending on the initial groundwater chemistry. Beyond sodium and chloride, which is the dominant cation and anion in these closed basin brines, they can have variable major cation chemistries, including calcium and magnesium, as well as trace elements, including lithium, boron, fluoride, barium, and strontium. On the left is a ternary diagram that's showing the calcium, magnesium, and sodium plus potassium concentration within brines from South America. And I just wanted to highlight the Atacama Desert brines shown in the blue polygon to emphasize the fact that even within the same system, you can have closed basin brines that are more enriched in magnesium, plotting up towards the center, and ones that are more enriched in calcium. So you do get a really wide range of magnesium to lithium ratios in these brines. And I think it's important to note that not every closed basin and not every sedimentary basin brine is enriched in lithium. The third type of brine is the geothermal brines. These are fluids that circulate through hot rocks, gaining to high temperatures, and that enhances mineral weathering and the release of solutes like lithium. The fluids in these geothermal systems can come from a variety of sources, including meteoric water, seawater, sedimentary basin brines, and magmatic sources. The heating of those fluids and the production of steam removes water and concentrates salts like lithium behind in the brines. The high temperature fluid rock reaction with sediments such as halite, volcanic materials, and basement rocks can contribute to the salinity, so adding things like chloride, sodium, and other ions. The circulation timescales of water through these geothermal systems ranges from hundreds to thousands of years. And just to give you a comparison of the water chemistry between two geothermal brines in Southern California on the left and the Upper Rhine-Graben on the right in Germany, we can see that the highest lithium concentrations are found in the hottest, most saline, sodium calcium chloride type brines that are also enriched in potassium. Magnesium is often depleted through high temperature reactions with clay minerals. The brines can also be enriched in a number of other elements, including barium, strontium, silica, fluoride, rubidium, boron, and other trace metals such as manganese, iron, zinc, lead, copper, cobalt, and cadmium. And this comes from the high temperature water rock reactions, as well as complexation with chloride, which allows them to remain in solution. So the final point that I wanted to make is, again, that there can be inputs of these different types of brines in lithium brine systems. So for example, in the Smackover Formation, which is at the bottom of the Gulf Coast sedimentary basin, we can see that the highest lithium concentrations are associated with the highest hydrogen sulfide, which in this case is coming from thermochemical sulfate reduction. So it tells us there's a geothermal source. And the fact that these brines are enriched in elements like boron, potassium, rubidium that comes from high temperature reaction with clastic rocks and basement. In a closed basin system in Argentina, we see that geothermal brines are being inputted to the closed basin through rivers that transport lithium out into the closed basin that then is highly evaporated and enriching lithium and other elements in that closed basin brine. So I'm going to end my talk with just the references that I've put in the slides if you want to take a screenshot. And thank you for your attention, and I'm happy to answer any questions.
Thank you, Jennifer. And we do have time for questions, so please remain at the podium. Just a reminder to the audience that you could submit your questions to the panelists on our webpage live stream. Look for the Slido box underneath the live stream video. Committee members and in-person participants, people here in the room, are encouraged to ask questions. Please raise your hand or your name card, and I will call upon you. So anyone in the room immediately have a question? Okay, here's one. Okay, Jennifer, given the relatively short timescales over which the closed basin brines formed, might we expect future deposits to be impacted by climate change related events such as drought?
That my group has addressed in the Southwest. And I think what we've seen from many studies is that if you have groundwater that's circulating on timescales of hundreds to thousands to sometimes millions of years, that climate change impacts such as drought is going to be felt far into the future. So we call that a long groundwater response time.
Okay, thank you. Larry, hello, Larry. Would you stand up, please? Can you go to microphone, please?
Still Larry. You didn't mention the effect of wall rocks possibly being leached lithium, in particular volcanic rocks, which appears in my world to be the most important source of lithium. So could you comment on that?
Sure. So the question is about the leaching of lithium sources such as volcanic rocks within, for example, closed basins or sedimentary basins. I think that certainly is a lithium source. I specifically didn't talk about that in my talk because I know that Madeline Blondes and Leanne Monk are going to talk more specifically and others about sources of lithium within these systems.
Michael.
Michael Manga, Board of Earth Sciences and Resources. Thank you, Jen. Could you tell us a little bit more about the sorption and desorption process and how engineering practices might influence those processes?
Yeah, that's a great question. Again, I didn't talk about it in my talk because I know that's something that Leanne's going to talk about and is really important in places like Clayton Valley, where the circulation of older groundwater, possibly geothermal, would have added lithium to clays, and then the circulation of a different water chemistry would have then enhanced absorption of lithium, and there's still a source of lithium within those clays. So I'll wait, if you don't mind, for Leanne to give us some more specifics.
And I've just been reminded that we have microphones on stand. So if you're in the room and you'd like to ask a question, please go up to one of these microphones. Jennifer, would brine derived, is there any reason we couldn't use brine derived from desalinating seawater as a source for lithium or other metals?
That's a great question. So lithium in seawater is not as high as it is, as I showed, lithium from within sedimentary basins. So you do get some lithium when you evaporate seawater, but then we're seeing it's much more enhanced within sedimentary basins, likely from leaching of these sediment or mineral sources. So I'm not sure the total concentration that you get from seawater, but you get higher from these closed basins and sedimentary basins is what I'm trying to explain.
Okay, thank you. We have some questions from the online audience. Have you considered, what's your opinion of the lithium resources in the Michigan Basin?
That's a good question. We published a paper recently where we looked at lithium across basins. And if I go back, I actually have a plot. It wasn't as high as some of the other places like the Appalachian and the Gulf Coast Basin, but it is elevated.
Okay, thank you. I'll bet that question was from John Yelich. You're in Arizona. The Mesilla Basin of New Mexico has some of the highest heat flow in North America, and it has elevated lithium concentrations. Is this considered an addition region for lithium extraction?
Yeah, that's a good question. So it's an area I've done a little bit of work on, not a lot. So I think that fits more in one of these geothermal input type systems. It has a brine that's coming up at the southern margin. I don't know the lithium concentrations off the top of my head, but yeah.
Oh, okay, well, thank you. Anyone else in the room? Doug Hollett.
Yeah, Doug Hollett. I've got a quick question that goes in the direction maybe of basin evolution. Because of the contributing factors that tie to the lithium concentration, is there evidence of zonation in basins? In other words, could this be another marker similar to hydrocarbon maturation in a basin? Could some of the brine chemistry also be a marker for basin history?
Yeah, that's a great question. So I'd say take a place like the Michigan or the Gulf Coast or the Paradox Basin. You certainly see the highest lithium in the brines that are residual from evaporation of seawater. And so there's a lot of indicators from the age, from the chemistry, the isotopes of the brines that tell us that these brines have been retained within the basins. And so there is a stratigraphic relationship. So it tends to be places, for example, shales within evaporite minerals that are a relatively closed system where these very dense saline brines can remain and have not been flushed by meteoric recharge, Where more open systems, margins of the basins, you see that more recent meteoric recharge has flushed that residual brine and the lithium concentrations aren't as high.
Okay, if I could just follow up on that, is there any relationship potentially then with geopressure? For example, in the Gulf Coast region where you might see sort of stepwise progression of brine chemistry?
Yeah, that's a good question. There's certainly the hydrodynamics is related because again, once you can get meteoric water in there, you're flushing, that high lithium that's built up over geologic time is not retained. And so there are some basins that have some overpressures and that prevents that meteoric recharge. Again, there's some lower permeability units where these residual evaporated seawater is retained.
Okay, thank you very much, Jennifer. We're ready to move on now. Thank you.
Okay, thank
Appreciate
you.
your talk. Okay, our next introductory presentation is from with the U.S. Geological Survey's Utah Water Science Center. Scott, take it away.
Thanks for that great bio, Margot. I've never really been one for writing in the third person, so okay. So let me just, I thought I would take the opportunity for us to talk about what is critical, okay? And in 2017, there was an executive order. There have been a few draft lists of critical minerals. One of the important things is the Energy Act of 2020, and kind of following that, we've narrowed down onto finalized lists now. You'll see the references there. One thing I would point out is these aren't really minerals. So that, a small point. And then in the 2021 revisions, I would say there were some additions and some subtractions from the list, uranium most notably, because it's considered a fuel material. And then the SPOF, single point of failure. These are elements for which there's one dominant global supply. And the methodology is quantitative, except for those kind of single points of failure, which is another criteria. And then, of course, if you look at what's critical, it's half the periodic table. Okay, so, and only a few of them are really related to minerals. So I think this is useful for us to consider. And then the final thing I'd point out about criticality is 8 of the 50 critical minerals are actually traded on the London Metal Exchange. So when we think about economics of research, we can't think of these like commodities, really. They must be considered as really specialty chemicals. It's a specialty chemical industry that drives most of this. So if we think about a lot of these as commodities, the economics really don't work quite the same way. And in fact, you might think that something's more secure when it's a commodity because it's actually a free and open market. And then another definition, since we can, what is a brine? And I think about this a lot because, in the process of dealing with extraction and development, environmental issues of brines, you often run into this kind of conundrum of a conversation. Well, what is a brine, right? And all I would point out here is, if you look at specific conductance on the x-axis, which is a measure of how water conducts a current, and the total dissolved solids on the y-axis, you get a nonlinear behavior, right? And if you start down near the origin, you have a linear behavior to some point, the water's becoming saltier. And then at some point, it becomes a different type of material, right? So one of the conversations that you have in these instances is, well, okay, then tell me the water content of your brine. Or, is brine just salt with a high water content? And these operational, so, I'm really a champion of an objective definition. It might be specific to a system, but something that would, work for regulators, managers, resource extraction companies, something that everyone could agree on, right? And then, of course, the other point I would make, this is just an example from the Great Salt Lake, but, mass budgets are really important, especially in closed basins. And the water and the salt budgets are coupled, but they must be treated separately. So there's water in that there brine, I guess I would say. And then quickly, I'll just show you, thanks again, Jennifer, for the good introduction to the different types of brine deposits. And then I took a screenshot here of the database that I'm sure Madeline will tell you more about. And then another one that we're working on the left there. Well, it depends. That would be your left. And those red outlines, so that's a database of lithium chemistry in the Great Basin. And those are closed basin brines. Each one of those red outlines is a closed basin. We're to the point now where we have about 20,000 lithium values, several million entries in this database. And just to show that these produced waters in the closed basin brines, they kind of inhabit slightly different worlds, but of course they're not exclusive. And then I thought, by way of analogy of a ternary diagram, we could sort of just quickly do a compare and contrast exercise about brine resources and what are the characteristics and considerations for producing critical minerals. So one thing I think you'll probably get out of this is every brine's different, right? So the diversity of brine chemistry is high in every possible type of brine. Critical mineral prospectivity. I'm of the opinion that the geothermal brines have the highest prospectivity, closed basin brines the lowest. When Leanne and I used to work on this in Atacama, I always called it the null model. We just take rainwater and run it into a basin and evaporate it, and what's residual? Not much. You start to add water-rock interactions, you get a bit more. So the closed basins, I think, have the lowest prospectivity. But of course, they interact with geothermal and other kind of reservoirs. The depth of the resource. Okay, so, sedimentary basins, oil and gas brines, typically deep. Closed basin brines, typically shallow. There's an age gradient there too. And then geothermal brines, right, especially actively circulating ones, they span every depth range you could imagine. And then the consideration as you produce these, what's the connection to the surface environment? In the closed basin brines, there's a strong connection. In fact, that's one of the things I'll talk about next is the connection between the genesis of the brine, the environment, and the extraction process. And then I would note in deep, like, in the Marcellus and these types of issues where they had environmental issues with produced waters, the interaction between these brines and the surface environment is really limited except during extraction, right? So that's one of the issues David alluded to earlier about what do we do with all this water once we start taking it out. And now I just kind of mocked up some ideas of where different types of brines in the United States, North America, might fit on this. And the point here is really that these are polygenetic. You're not going to find anything that's perfectly on a corner here. And they inhabit this kind of polygenetic world, which is sort of how I think about the genesis. And then to kind of further the point Jennifer made, in a single system, you can have an immense diversity, right? This is just something hypothetical I put up from, brine aquifers, and some of them you might consider reservoirs deeper in the Salar de Atacama Basin. So there's a wide diversity within a single system as well. And then if we think about producing these brines or extracting things from them, the closed basin brines, the challenges are environmental and economic. Does it have an economically recoverable concentration? What are the environmental impacts? In the other brines, it's often technical and economic. And of course, the economics are related to the environment and the technical issue. And then the other issue is water availability for, extraction of minerals. And that's not only quantity and quality, it's also timing. Oftentimes in the Western US, when can you have the water actually becomes an issue of consideration. So then I just since the environmental issues, the economics, the extraction, and the genesis are so related in closed basin brines, I thought we'd just take a quick look at the trade-offs in exploiting these types of brines. And so they're generated in pretty harsh environments, right? This is an example. This is a Salar de Atacama in Chile. Samples there of what it looks like to mine these brines. And then the point I want to make about these godforsaken places is they're huge and the real estate is cheap. Okay. So if we compare how much that you would never have, you can see these extraction facilities, they would cover the whole island of Manhattan. You could never afford the real estate. And if you look at the area and the money that's made in a year from that, it won't take you far. Great Salt Lake, it's bigger. Its economic impacts are kind of wider, well beyond lithium and other things. And it still doesn't even touch the scale of, you couldn't do that with high dollar real estate, basically. And then that brings me to another point, about sort of the passive nature of extracting these. And I'm just showing you an oblique aerial photo here of the Great Salt Lake. There's a north arm and a south arm separated by a railroad causeway. The north arm is at halite saturation. The south arm is about halfway there. And they're connected by one opening, one breach in this railroad causeway. And you get dense north arm brine flows south through this opening, and less dense south arm brine flows north through this opening. So in an open channel, you have stratified and bidirectional flow. And so, we've done a bunch of work looking at how much lithium mass is exchanged here. The key thing to remember here is all of the freshwater inflows come into the south arm. And basically the north arm has no inflows, save some salty groundwater and a bit of precip. So this is an evaporatively driven pump that basically circulates these brines in a passive manner. And then one last example from the Great Salt Lake here, and that's in the colored symbols, plotted over gray symbols from the Salar de Uyuni in Bolivia. You'll see on the x-axis calcium to chloride. So as that ratio goes down, and you'll see in the lower right-hand corner inflow waters from Great Salt Lake. And then I'll just show you here the magnesium concentrations in the clusters for the north arm and the south arm brine. And we know that the north arm brine has a residence time of 2 to 5 years based on measured flows and the known volume. And you see the magnesium to calcium ratio goes up as the calcium to chloride ratio goes down. Chloride's conservative. We're concentrating the brine by evaporation, but we're also precipitating huge amounts of carbonate. And so this is there's a lot of talk about the enormous CO2 sink that this lake is as well, which is another interesting piece of the mass budgets. And then quickly, some considerations over the years that we've run into for responsible development of resources. You need numerical models to get people to buy into them. You need a conceptual model that underpins it. And then you need mass budgets for all kinds of stuff, including reagents, products, waste, if you want to do this responsibly and well and understand the impacts. And then this is some work I did with a colleague of mine. The references is down there. He's not bad for a lawyer. And we had a lot of fun working on this. And one of the things, that I would say is we realized you must measure and you must monitor. You need budgets. Borrow, it's a shared resource. Cumulative impacts are important. And then, borrow the idea of unitization from the oil and gas industry. It's a common pool resource. Are we going to share in the profits? How do we, not compete, but cooperate? And then I was just gonna end here by showing you, this is a matrix of lake characteristics in the Great Salt Lake. And then you see a vertical dashed line is lake level. And then each of those bars is a different consideration that's essentially managed for. And if you look down underneath economics, there's one line for mineral extraction, right? So this is a kind of a multiple use managed system. And in the example of Great Salt Lake, magnesium is the primary mineral they mine. And it's basically a single point of failure. This is the key source of magnesium for aluminum alloys, for defense, basically, aircraft and things like this. And the lithium that people are producing out of there is just a byproduct from years of waste and a new waste stream. So, and magnesium is a critical mineral. So just another way to think about this. Water availability, then I would say, is the number one issue. Passive approaches to brine concentration are really effective and simple. They're not really in vogue, and you need cheap real estate and other things, and there are issues. And then, of course, the deeper and the hotter we go, the greater the technical challenges will be. And with that, I think I'll stop. Thank you.
Thank you, Scott. We do have a few minutes for questions, and I've got one right here, and then we're going to go to Alex. With the commercialization, I know you're a hydrogeologist. With the commercialization of sodium-ion batteries ramping up, do we expect the criticality of lithium to slack off over time? I know you've thought about this.
Well, you know, in one of those papers that I wrote with my colleague, the lawyer, you know, the USGS had a massive lithium program in the 70s after the Iran fuel crisis and all of this. And I think one of the things that I've learned by kind of watching that and then being re-involved in a new generation of this, we all knew that lithium was going to be useful for energy storage in the 70s, but scaling things from the bench top to a continental scale industry is a completely different issue. So, you know, and I think, I mean, I look at lithium recycling companies that are starting up that think they're going to recycle batteries. And you look at the effectiveness of lead acid battery recycling and you think, it's probably going to be a pretty good option for a good long while. Yeah.
Okay, Alex.
Hi, Alex Klaus from the Committee on Earth Resources and a lawyer.
Nice to meet you.
You too. So I actually have two questions. One is, how comprehensive is our mapping and data regarding concentrations of critical minerals in U.S. brine? So like, do we have more information on federal lands versus non-federal lands or certain parts of the country? So I'm just wondering how much mapping and data do we have? How much more do we need? So that's one question. And then the second one, is the regulatory regime governing extraction of critical minerals from brines wholly dependent on, is it on federal lands versus state lands, or is there some overarching sort of set of regulations that is either being developed or has been developed?
Well, first I would say Madeline will probably talk some about her produced waters database, which is, you know, obviously, you know, a huge amount of industry data there and not much in the Western US. And there's quite a bit of information in there, but, you know, and then I would say in the same vein in the Western US and other things we've done, when we started looking at lithium, we also pulled tungsten because the USGS Mineral Resources Program had some interest in tungsten at that point in time. But in terms of the whole rainbow of 50 elements, I think that's severely lacking. And, you know, in the database I showed, we have federal, state, you know, all kinds of, there are 7 or 8 different databases that have been ingested. But sort of unification of that and looking across the other elements, I think is a need. Second question was?
The regulatory regimes governing extraction, whether they exist, federal, state, or is it totally dependent on federal lands versus non-federal lands?
Well, at least in the Western US, right, it all boils down to mining law. And so from state to state, it's different. Typically, the water rights across states are very similar. But you know, and Nevada has, you know, locatable and leasable minerals and a mineral mining law of 1872. And it gets really complicated. And I think one of the neat things with brines is there is an opportunity potentially to stop being reactionary and avoid some of this path dependence and litigation and maybe even compacts. Examples like that would be really useful because there's a lot of transboundary issues. But it's all going to boil down to the state mining law, I think, at least in the Western US. Yeah.
Okay, I see a hand raised on Zoom. Elizabeth Holly, can you please turn on your microphone and ask your question?
Yeah, good morning. Elizabeth Holly from the Committee on Earth Resources. I'm wondering if you can give us both the historical perspective and perhaps your forward-looking opinion on the potential for lithium recovery as a byproduct of magnesium versus from salar brines like production at Silver Peak? How do those numbers compare?
Can you repeat your question, please?
Oh, sure. I'm wondering if you can give us both the historical perspective and perhaps a forward-looking opinion comparing the potential for lithium recovery as a byproduct from magnesium versus salar brine production at Silver Peak and perhaps other types of brines going forward. How does byproduct lithium compare?
Well, the first thing I'd say about Silver Peak is they got lithium as a leasable mineral. They didn't do anything locatable. They have no claims to anything else. So they have big piles of potash and other things that might have some value that aren't being moved because they never claimed that. So there's a lot of, this is waste as a resource, another thing that USGS is starting to work on quite a bit. And then, for example, in Great Salt Lake, they mine a bunch of magnesium. There are multiple companies that do this, and they both have brine as waste, and it's mostly interstitial brine and salt piles, and it's very high in lithium concentration. So they've got 20 or 30 years of mining sitting there on the ground in lined ponds as interstitial brine in salts. So, I think in the near term, they're going to be using 30 years of evaporation as a head start. But, going forward, Compass Minerals in Utah had a whole lithium line coming online. They were going to produce in parallel with their magnesium they use for fire suppressants and road salt. And they just pulled the plug on that. And I think the challenges of the high magnesium brine, they were trying to use DLE and other things. And I think that's still an issue. I think at least in that instance, the lithium is a waste product that, can accumulate probably, but it's going to be a challenge to mine them in parallel, I would guess.
Okay, thank you, Scott.
Thank
There
you.
are many, many good questions. Obviously, a rich topic here, but we need to move on. So I'm now going to turn it over to Michael Manga, who's a member of the board on Earth Sciences and Resources, and he'll begin our next session.
Thank you, David. And as David mentioned, I'm Michael Manga at the University of California, Berkeley, and a member of the Board of Earth Sciences and Resources. Our next three speakers are going to address domestic resources, and we'll save our questions and discussion for a panel discussion after all three presentations. Our first speaker is Madeline Blondes. Madeline is a research geologist at the U.S. Geological Survey, Geology, Energy, and Minerals Sciences, Minerals Science Center in Reston, Virginia.
Okay. This is the move forward button. All right. Thank you. My name is Madeline Blondes. I appreciate being invited to this event. Today, I'm going to talk about lithium in sedimentary basin or oil field brines. Jen McIntosh gave a great introduction there, so I'm going to jump off from that. I'd like to acknowledge my colleagues and the U.S. Geological Survey as well here. There we go. Okay, I'm going to talk about 5 main things today in this short talk. The first is lithium potential from existing waste streams. And so this gets to David Spears's question earlier. There is when you're using existing waste streams, you can potentially have lower impact. And so I'm going to show you some calculations of basically how much lithium has been coming out of the ground just from oil and gas production itself. The next is the origin of high lithium in sedimentary basin brines. And I'm specifically going to talk about the differences between what I'm calling shale, so basically shale plays are things that basically need to be hydraulically fractured, and conventional reservoirs. This actually gets a bit to Doug Hollett's question. I think there actually is a very good analogy here with oil and gas movement and water itself. And there are some obvious differences between shale plays and conventional reservoirs. I'll also talk a bit about spatial heterogeneity. If a given formation has high lithium, is it high everywhere? And then I'll talk about a recent model where we're basically predicting the lithium resources in the subsurface using machine learning. And lastly, quickly, I'll touch on co-produced commodities and also co-produced hazards, you can call them, things that are also coming up from the subsurface during lithium production that could either be helpful. That moving? I see some bubbles? Yes. Okay, so the first thing I'm going to show you and talk about is lithium from existing waste streams. So this is not the subsurface. This is what's coming out of the ground. So on the left is water production as a byproduct of oil and gas production. And it's basically summed to different counties. This is a cumulative number. So you can see it's going from 1980 to 2023. So it's just over 50 years of production. On the right, this is data from the USGS Produced Waters database that was mentioned. And to answer your question, it's almost entirely industry, at least this particular data set. It comes from oil and gas producers. And so areas that are darker, the darker purple, are areas where there's the highest lithium. Next slide is how we actually are combining those to get estimates of lithium coming out of the ground. So is that cumulative total from 1980 to 2023, and then we apply the average lithium concentration from the database, and this is for a given county. So there aren't a lot of places where you have this information for a given well, but we can average to counties for both of them. And just to give you some context here, the scale or the color bar here, the kind of bright blue or the blue, and that's fairly low lithium. We're looking at, one of those counties in the 50 years of production from that waste stream could have produced batteries for 1,000 electric vehicles. So that's not a lot. As we move up in color here, we get up to the green. We're talking a decent amount of lithium, and you should notice here that some of these, even though it's not particularly high lithium in the, say, Permian Basin in West Texas, New Mexico, there's just so much water that there is still an appreciable amount of lithium coming out. And so the green counties are comparable to, 1 year of lithium consumption. And if you start getting into the yellow, you're looking at the global producer of lithium. So, all of Australia's lithium production. But again, that's 1 year compared to what's come out of the ground for 50 years. So it's still a significant resource, what's been coming out of the ground and then hasn't necessarily been used. And that can potentially be used. The next thing I want to talk about is the origin of the high lithium in sedimentary basin brines. And I want to highlight the differences between shales and conventional reservoirs. I'm using shales as I shouldn't say a convention when I'm comparing it to conventional, but I'm using shale, talk about shale plays, anything you have to hydraulically fracture. It can be, you have shale in it. I know a lot of these are not technically shales. And I'm highlighting here, the vertical line is 100 milligrams per liter lithium concentration, which is a ballpark economic level. It can be economic at lower concentrations, but I'm using that to just give some context. It's only the Marcellus that regularly has concentrations greater than 100. The other, there are others like the Eagleford only has a couple data points, 2 data points that show elevated values, most are not. And then in the Appalachian Basin, the Queenston has a couple data points as well, but it's mostly the Marcellus. Most of the lithium from oil and gas basin brines, or these deep sedimentary basin brines, comes from conventional reservoirs. And so this is a plot, again, just showing lithium concentration. You'll see the 100 milligrams per liter boundary. It's kind of in 3 sections. The top is Gulf Coast, Texas area. The middle is the Appalachian Basin, and the bottom is the Williston. So there are quite a few plays, and I should mention triangles are those shales. There are quite a few plays beyond the Smackover, which is the most well-known one, that have high concentrations of lithium in them. Okay, so one thing it's important to understand, when people have looked, there have been a number of studies looking at why we get, why lithium concentration, and it seems to definitely be a function of the amount of lithium in the rock and things like temperature, thermal maturity, depth, and those 3 things are related. But for shale plays, the lithium is definitely a function of the lithium concentration in the rock. For the conventional reservoirs, the place where we've seen oil and gas move as well as water, the rock lithium does not determine the concentration of the lithium in the brine. Most of those reservoirs are not high lithium reservoirs. The Smackover is not particularly high lithium, the rock itself. And so there has to be another mechanism. One thing that is possible, we see that in many cases where lithium is high, H2S, so hydrogen sulfide, dissolved hydrogen sulfide, is also high. And when that happens, metals are also really low. And this is because once you have hydrogen sulfide, any base metal will immediately precipitate out a sulfide mineral. And so, this led me to think about, okay, can we actually compare those two? Is H2S a driving factor? Unfortunately, beyond the Smackover, there's almost no data. And so where there's actual measurements for single samples. And so here this bubble plot here is comparing the reservoirs. So there's a separate lithium data set and a separate H2S data set. Size on both of these is related to the concentration of either lithium or H2S. The color, the first thing that stands out are those green ones. Those are Appalachian Basin reservoirs, and there's no comparable H2S data. There are like 2 data points in the whole Appalachian Basin that I could find for this. And then the gray dots are ones that are generally smaller, either less lithium, less H2S, and I'm kind of ignoring them here, but to show you that there are many reservoirs with much less of both. And then when you look at the remaining ones, you can kind of match the colors of these big reservoirs. So Smackover in red. I actually can't read my own slide from here. There's the Madison in pink, and I'm going to show both of these on the next slides. I think one of these is actually a Michigan Basin one that's relatively elevated, but again, I can't see my own slide. Okay. Oh, so I mentioned it here. Yeah, basically Smackover, Jupero, Red River, Madison, Edwards, Permian. So there are a number of reservoirs that have both high lithium and high H2S. I'm not going to get into this in much detail, but for places where lithium has been put into for places where lithium, there is a source for the lithium, whether or not it's volcanic, from any number of different high lithium crustal sources. If you do have high H2S and potentially high temperatures in these settings, actually keep that lithium in solution. Spatial heterogeneity, one of the questions, if there's high lithium in one reservoir, do we see it everywhere? Left is Appalachian Basin, right is the Williston Formation, left is above 100 milligrams per liter, right is 50. So if you look at the green is the Marcellus, the yellow on the left, or the orangey yellow is the Clinton. On the right, keep an eye on the pink Madison. So now if we look at the entire sample set, we can see, particularly in the pink Madison on the right, even though you might say, okay, the Madison has high lithium, when you go to look at different regions within there, there are some places where it's quite low. So it's definitely not constant. For the shales, in many cases, it's, for example, the Bakken, which is relatively low, but it is much more constant. Okay. This is a study. So my colleague, Kathy Knierim, just finished a paper that's been submitted. And so basically it's using machine learning in the subsurface. So now even though this paper did include also what's coming out of the ground from oil and gas production, I'm focusing now on the subsurface resource. And so this is an important model because it's using geologic and geochemical variables to predict lithium. So even though lithium concentrations in the brine were used in the training data, we can actually predict lithium from the geology itself. So using things like, thicknesses, depths, temperatures, lithology, et cetera. And so one outcome from this study, she found that the subsurface lithium resource that's down there just in southern Arkansas, so this is not the whole Smackover, just in southern Arkansas could meet 10 times the IEA estimate for 2030 global annual lithium demand for electric vehicles. And the other thing she found is that hydrogen sulfide in this region is in fact an important driver of the Smackover high lithium brines. And lastly, co-production. So are there other commodities when we look at high lithium? If those high lithium brines are in fact associated with high H2S, you will get almost no metals in them. This is a hard thing to plot and show because most of them are below detection. So the data that do exist don't really tell the whole story. It doesn't mean that if you have high lithium, you won't get high metals in certain places, but if it is associated with high H2S, and it is in many cases, then that is not something that you can co-produce. Another thing is bromide. I'm not going to get into detail about that, but often where you have high lithium, you also have high bromide, although it's not a direct relationship. And magnesium, this has been discussed in the last few talks. Magnesium is important because it can interfere with direct lithium extraction technologies. The plot on the right is showing in size the lithium concentration, and the color is the magnesium to lithium ratio. So actually in the Smackover, like in southern Arkansas, you actually have a fairly low magnesium to lithium ratio, meaning that there would be less interference with direct lithium extraction. But in other places, Michigan Basin, Appalachian Basin, you have much higher magnesium there, which would just increase costs. Lastly, hazards. I've been mentioning hydrogen sulfide. It can kill you at very low concentrations. We have to be very careful when we're sampling this. And, you know, if there is that association in some of these places, that's something that needs to be considered when we start producing. And then also many oil and gas brines have naturally occurring radioactive material in quite high concentrations of those, particularly say the Marcellus shale. So radium is quite high there, and also in a number of conventional reservoirs. So that also is something that needs to be factored into both environmental impacts and costs. I believe that is it. And thank you.
Thank you, Madeline. We're going to be saving our questions for the panel discussion after all three presentations, so come and grab a seat next to us. Our next speaker is Pat Dobson. Pat is a staff scientist in the Energy Geosciences Division at Lawrence Berkeley National Lab in California.
Hi, it's great to be here. Talking on behalf of my colleagues at Berkeley Lab, at UC Davis and UC Riverside, at MIT, at Geologica, and also UC, the University of Auckland in Australia, who did a lot of our reservoir modeling for this work, and also thank the Department of Energy for funding this effort. So I'm going to talk briefly on our project on geothermal brines, focusing on our work at the Salton Sea. So in the context that we've heard a lot about the three different types of brines, closed basins, sedimentary basins, and geothermal brines. And what we've seen is that geothermal brines have long been recognized of being a source of potential different types of critical materials, such as lithium, and that elevated lithium concentrations are found in just studies that have been done in the Rhine-Graben by Bernard San Juan and his colleagues have shown that there's a number of extensional areas such as the Rhine-Graben that have elevated concentrations of lithium, and we see similar sorts of things at the Salton Sea geothermal system. We also see that there are elevated metals, unlike what Madeline just discussed, that are present in a lot of these geothermal brines as well. Next slide. Go here. Whoops. So I want to briefly just mention the geology of the Salton Sea area. It's a complex geologic environment. It's going to transition between the extensional tectonics we have in the Gulf of California. We have a spreading center transitioning to a strike slip margin between the Pacific Plate and the North American Plate. And in this area, we have extension. We have quite a bit of high heat flows, and we have volcanism in this area. Due to the extensive amount of sedimentation that's sourced by sediments coming from the Colorado River system, this area is periodically inundated with water and with sediments that are really key components to this system. So it's a really nice sort of brewing pot for creating ideal conditions for this type of system. So some of the previous presenters have talked about questions about where does the lithium come from, and here we have a number of potential sources. We have the sediments and the waters that come from the Colorado River's drainage area. We have surrounding basement rocks that can shed its sediments into this basin. We have volcanism, so we have volcanic rocks and their associated fluids that are sources of lithium. And then we, due to this fact that it is a closed basin, we have the ability of evaporative concentration of the waters to form salar-type brines. Some of the processes I mentioned are rifting, substance erosion. We have repeated flooding of this area. And we can see on the sort of the bathtub rings of the ancient Lake Coahuila that's formed and evaporated in the past. We also have weathering and leaching that's accentuated by circulating hot geothermal fluids and hypersaline fluid circulation in this area. So one of the things that our team wanted to do was to get a constraints on the resource potential for the Salton Sea geothermal reservoir. And so this is just a graph showing porosity measurements were made on a sequence of core samples that were collected from a variety of wells in the Salton Sea geothermal field. We can see the increasing with depth, we have decreasing porosity as you would expect from compaction and from diagenesis and metamorphic activity that's reducing the pore space. We can also use the look at the fluid chemistry that's been collected to get an idea of the lithium concentrations in these brines. So if we put this all together, we can come up with answering the question of how much lithium is present in the Salton Sea geothermal field. And these are three different ranges of estimates that we came up with. First one is looking at the proven reservoir, that is the produced geothermal field that's been in operation for over 40 years in this area. And that's shown in the outline in white. That footprint is a little over 30 square kilometers. We have a reservoir thickness a little over a kilometer, and we have porosity of around 11%. And so then we can go and calculate how much fluid is present there. We have about 200 ppm lithium in the brines. And we come with an estimate of a little over 700,000 tons of lithium metal. If we look at the sort of the red outline, which is the probable the extent of the geothermal reservoir, that gives you a bigger footprint of a little over 90 square kilometers. We extended the reservoir thickness a little bit and also bumped up the porosity to take into consideration the fracture porosity in addition to the pore space porosity of the matrix. And using the same lithium concentration of 200 ppm, we come up with about tons of lithium metal. We also then did an intermediate estimate, which is accessible, and we just basically excluded the area below the Salton Sea to come up with that value. So one of the things to think about is this is the resource that's in place. It doesn't necessarily mean we can actually recover from this area. Another big critical concern, I think some of the people speaking after me to address this is what is the technical capabilities of using direct lithium recovery? It's never been done on this sort of commercial scale. They're producing on the order of like 50,000 gallons of brine per minute, and that's a lot of brine to process to recover lithium. So just looking at the Salton Sea geothermal resource in current context, we've been producing from this geothermal field for over 40 years. Over the last 20 years, the production rates have been fairly constant. And so if you just take the amount that they produce from the geothermal reservoir currently, and you look at the concentration of lithium in those brines, it would be equivalent to 21,500 metric tons of lithium that's coming up to the surface and then being reinjected back underground. If you look at it in the context of the graph on that's equivalent to more than 10% of the world consumption of lithium today. So it's a huge potential resource, and that's only a fraction. They're only producing, the developed field is about 400 megawatts. Their plans to up that to 800 megawatts of geothermal production, which would double the potential lithium that could be produced from this field. So that could really fill in the gap between the growing predicted demand for lithium and what we have available at our currently. So this is a depletable resource. And we've done some reservoir modeling to sort of assess how much lithium is going to decrease with time as we reinject lithium poor brine back into the reservoir. It's going to decrease the concentration and decrease the amount of lithium that can be recovered. And these curves are showing you the solid line is using the existing well field with injection and production wells as they currently are oriented, and then taking and putting in lithium, the injection wells further afield. In the past, the reservoir was sort of managed with the idea of producing heat for generating steam. And now we're concerned with chemical breakthrough because we're producing a chemical commodity from these brines as well. So it's very clear that it's really important to do an optimal way of recovering the lithium from the geothermal field. And we can see from these curves that you could enhance your lithium production by 30% just by moving the location of your injection well so that there's a greater distance and more time between the fluid that's reinjected is showing back up at the production wells. So one of the other questions that our colleagues at UC Riverside have been focused on is looking at where is the lithium in the brines, and it's present in the minerals phases. The average lithium contents of the rocks range between usually about 40 to 80 parts per million. There's a lot more rocks, 90% rock, 10% porosity space. And so that adds up to a lot of potential lithium that could potentially recharge this system. In analyzing this, and we used a laser ablation ICP-MS to analyze the lithium in the different mineral phases, we see that the lithium is primarily concentrated in hydrothermal chloride. And so it seems like it's primarily in the octahedral part of the mineral. We're planning on doing some experimental work with colleagues at UC, University of North Carolina, Charlotte, to get some better thermodynamic constraints. Right now, we're using end-member values for cookite, which we are not sure is really an appropriate end-member because of the issues of solid substitution. So we can see that the variety of different potential sources, we've measured the lithium in the volcanic rocks and the sedimentary rocks, and we're planning on augmenting this work in our next phase of our study. So ongoing research, we're going to be reservoir modeling work with improved gridding resolution and assessment of different options. We're also working, I didn't mention this in this presentation, we're doing a variety of looking at impacts of water use, chemical use, air quality, induced seismicity, and a variety of other potential impacts. Real big focus on water use because that's a big concern in this area. It's really affected by all their water comes from the Colorado River with the long-standing drought. There's going to be reduced allocations to the different western states, and that could impact Imperial County. We're also looking at other critical materials within the salton brines and what the potential is for doing extraction of multiple mineral phases to provide additional resources. And then also, like, as I mentioned, looking at the constraints of lithium water rock reactions to see whether or not there's potential that they could sustain production from this resource. We're hoping to contribute to the USGS's effort for assessing the national lithium resources, and then also continuing on with community engagement. So that's it. Thanks very much. Yep.
Thank you, Pat. I forgot to turn my microphone on. Our next speaker is Leanne Monk. Leanne is a professor of geochemistry and geological sciences at the University of Alaska, and she's also director of the Alaska Critical Minerals Cooperative.
Thanks, Michael. All right. So yeah, I'm Leanne Monk. I'm a professor of geological sciences. I'm a geochemist and a geologist, and I've been working on closed basin lithium brines for about 14 years. So just a quick outline here, and thanks, Scott, for mentioning the elements. So I'm going to show you a little bit about, where lithium is produced from, kind of step back a little bit and look at distribution of where lithium is actually being produced in terms of hard rock, brines, and what's called other. I'll show you a new compilation that we have in review right now on the global distribution of lithium brine deposits. I'll talk a little bit about what I call the geologic recipe is for the closed basin brines, and we're in the process. My extended research group, including folks at Brown University, UMass Amherst, and UT Dallas, are all working to update the original ore deposit model for the closed basin brines, and we're starting to incorporate other information about the low temperature geothermal and high temperature geothermal, which you just heard about from Madeline and Pat. And I'll talk a little bit about what we consider in terms of what controls the size and distribution of some future R&D that my research team has been thinking about. And then water and lithium. It was already mentioned that water is a really important part of what's happening with brines, and not just the brine, but the fresh water. So that's the general layout. So this plot is showing you the distribution of lithium production. Okay, so currently most of the lithium that's out on the market is coming from pegmatites, spodumene, hard rock. However, most of the global resource is within the closed basin brines. This is the global distribution of these three that you've been hearing about. we're proposing to kind of bring together and standardize. It's good that we're all here together. Maybe we can talk about how we're going to describe these and name them. So we're proposing closed basin, which are the salar type, low temperature geothermal, which are those associated with the oil fields, and then high temperature geothermal. So you can see that most of the lithium brines are actually concentrated in these mid-latitude regions. And those are dominated by the closed basin brines. So this is the original ore deposit model for closed basin brines, and it was generally modeled after the Salar de Atacama in Chile, and but that's mainly because most of those types of brines occur in South America. But you can see here that there's 6 main characteristics that we had identified, and we're working to update this now. But an arid climate, closed basin with a salar or salt crust, some kind of geothermal activity. We could start talking about hydrothermal as well, either happening in the past, the present, perhaps both in some cases. Tectonic subsidence is very important because you have to create room for the solutes and sediments to fill in the basin. Lithium sources, this has been raised already today. And in the case of the closed basin brines, most of the work that has been done so far points very strongly to ignimbrites, volcanic rocks, as being the primary source, which are then leached by low temperature geochemical processes, move through the groundwater, can also be not just within the basin, but intrabasin, and get concentrated. So this concentrate, the processes like evapotranspiration to contribute to that concentration are really important. And we're adding a 7th characteristic in the work that it's actually in review right now. And that is specifically the hydrogeology. So the hydrogeology plays 2 major roles. One is basin hydrogeology and how the lithium is leached in the groundwater and brought to the basins, to the floor, to the shallow when we compare to like low temperature oil and gas related brines. And the second is if you don't have recharge, you don't have production, okay? And it's really important to also consider all of the water resources in these basins. It's not just the brine that has the lithium or whatever element you're concerned with. You have to consider what are the relationships between freshwater, climate, and this resource. So this is the updated block model that we are working on, and it shows not the relationship, but it shows it's hard to do in one block diagram to show all that geology, but it shows the types: the closed basin salar, the low temperature geothermal or oil field, and high temperature geothermal, such as the Salton Sea, which Pat just talked about. And I think it's really important to consider the comparison of the lithium concentration. So this graph shows the mean lithium concentration for the 3 types. So the closed basin has the highest concentrations that we know of so far, compared to the low temperature geothermal and a high temperature geothermal. However, those 2 emerging types of lithium brines are considered, this is simplifying it, but the idea is that there's a lot of it, right? They're high volumes, low concentration compared to salar type brines, closed basin brines, but potentially very large volumes. So this is a graph of the mean lithium concentration, basin floor area, basin elevation, and total resource. And so this is just for closed basin brines. This is the map that I showed you. That's a global compilation of all brines, but this is just for the closed basin brines, which do hold the largest resource globally. And what we see we look for ways, to help with exploration and other parts of, other interests. And so we take, we have these very large data sets, but these variables here are one thing that we've noticed. There is some relationship to the total resource that is actually held within the individual basins. And of course, there's some outliers. And so the next point I want to make, what else do we need to be doing? So based off of what we have been doing, I've identified some areas that I think are critical to continue more work and to put more resources into. So exploration at the basin scale and in the subsurface. Okay, so this is a really interesting situation with these lithium brines. Like Scott pointed out, these are chemical processes that are happening. It's a liquid resource, and it requires some different approaches that are more typical in other mineral commodities. The brine and freshwater hydrogeochemistry. So Jen talked a bit about chemistry relationships between different elements. So it's that plus it's the processes. So it's linking, where did the lithium come from? What are the rocks that you can remove it from? And then what are the processes that happen to that water, that brine, over time that contribute to concentrating it to different levels? And of course, this then all leads into a really important thing, which is calculating what is the resource, right? So the last thing I want to mention is, and our research team is heavily focused not just on understanding lithium brines as a resource, but the issues of water in the environment. And it's the water sources, water types, water scarcity, water availability. And so this could be a whole workshop in itself, of course, but I wanted to end with that. So just in summary, closed basin lithium brines hold the majority of the global lithium resources. The low temperature and high temperature lithium brines are emerging along other category, which is really volcanic sedimentary deposits. Pegmatites are currently the lead in global production. And each one of these brines, no matter which category it falls into, has complex geology, hydrogeology, and geochemistry that control the formation. And every basin is unique. So you heard that in some other ways earlier. But it really does require an individualized approach to exploration, production, and sustainability. And water resources are, and the availability of water are really the most important environmental consideration that kind of drives all of the other aspects that we think of in the environment. And I have questions on my slide, but Michael's going to tell me to sit down.
Thank you, Leanne.
And the references.
Okay, so we have until 12:45 today for our panel discussion. So that's just slightly under 20 minutes. A reminder to the audience that you can submit questions for the panelists on our webpage live stream. So look for the Slido box underneath the live stream video. And committee members online or those in the room, you can raise your hand or turn your name tag on its side, and I'll call on you. And maybe to get started, we have lots and lots of questions already. So I'll start with a couple, and then we'll do people online, and people like Doug are already chomping at the bit with his name tag. But thank you all three panelists for those lovely presentations. So the presentations today focus on settings in which we're already extracting fluids, right? Geothermal systems and oil and gas fields. Given what we understand about subsurface brines, are there settings or formations that have the potential to be economic resources that are poorly understood or poorly sampled because they haven't been previously used as a resource? Leanne, for example, you mentioned ignimbrites as being a source of lithium, and we don't do a lot in ignimbrites, for example, Yellowstone. So anyone on the panel can address, or all of them.
Okay, press and then release. Okay, it's like fishing. I would say to that, one area that I think is underexplored are actually buried salars. And so the closed basin type of lithium brine that I just described, there's ideas that some of those older have been buried and may or may not still contain the lithium brine. And then with respect to what Michael pointed out with the ignimbrites, so we know that volcanic rocks can contain high concentrations of lithium, like a pegmatite, which is similar sometimes in composition to a peg or to a ignimbrite. However, it's cooled much slower and deeper within the crust. But ignimbrites they're very voluminous and large. They're near surface. And so they actually do have a lot of attributes that people who do mining and exploration may be interested in. However, when you compare that to lithium brines and closed basins, the advantage there is the lithium's already in solution. And so if you can mine lithium from something that's already a fluid, that's advantageous from a production standpoint.
Madeline?
So I would say within oil and gas brines, there's a decent amount of data, and there are definitely a number of potential formations that could be good targets. One thing to note is that we are data limited by where there's oil and gas production. So even just off of, there are places that we've been looking and we say, oh, what's going on? Just there's no, producing oil and gas wells where we can get samples. And so I think that there's definitely, and this has been happening, frankly, in the Smackover where people are potentially opening up older wildcat wells to test for lithium. So I think, and then in addition, I think there's a decent amount of data as far as which formations have lithium, but as far as understanding where it might be within there are definitely data needs as far as understanding the different parameters, including H2S, to try to potentially prospect.
Pat, did you want to add anything to this discussion about unappreciated sources? Or otherwise, I'm happy to go on to the next question, which maybe you can start us with. Scott in his presentation made, I think, a pretty provocative statement. He said, geothermal brines have the highest prospectivity. And I'm wondering if either of our three presenters would like to debate or challenge that statement. I mean, in Leanne's presentation, she showed that the concentration and volumes, for example, in some of the other settings were substantially higher.
Sure. So I would say that I would say that there's some challenges with geothermal brines because they have to remain at high temperatures when you're removing the lithium. You can't let them cool because of the high concentrations of all the dissolved materials. If you're going to re-inject the brines for them to stay in solution, the brines have to stay at around 100 degrees C, and so that's a technical challenge. The advantage of geothermal brines is that you're already producing them. So you don't have the wells are already in place, and so if you can just tap into it, it's sort of adding on to the process in a much easier fashion. So I would say, in Scott's viewpoint, we already have one leg up on it. We're already producing these fluids. The challenge is the extraction part, and I think some of our subsequent speakers are going to address that challenge.
Madeline?
I feel like we should be standing in a triangle like
Yeah.
that Trinity kind of thing.
No, we're looking at each other rather than all the people on Zoom.
So for oil and gas brines, I think similarly to what you said, the fact that there's an existing industry, there's existing infrastructure, particularly in regions where we're thinking about the energy transition, moving from oil and gas. So, there are reduced costs in that sense. It's already coming out of the ground. There's already a local buy-in, which I think is quite important too, because it can be hard to say create a new pegmatite mine. And then interestingly, I like Leanne's framework of the low temperature geothermal versus high temperature geothermal, because it's true. Many of the oil and gas basin brines are low temperature geothermal, and they do get up a bit higher than what was shown there, in the hundreds. So I think in that sense, similarly, there's that existing infrastructure that makes it a really good target.
Just quickly, and it was a log scale, so it did show hundreds, but I think I would ask Scott to maybe define what he means by prospectivity, because I think we're on the same page.
Well, when I wrote that, I was thinking there are 50 critical elements, and the widest variety you're likely to get is in hot water that's interacted with a bunch of different types of rocks. So certainly there are technical challenges. From the lithium point of view, I think, closed basin brine with a geothermal input's probably highest prospectivity. But, I was thinking of the rainbow, the full spectrum of elements. I think I would be curious what you guys think, but there seems to be a wider range of compositions in geothermal brines.
Thank you, Scott. Okay, Doug, you've been very patient.
So I'm just curious about the possible intersection with other kinds of mineral systems. Appreciating that, as Scott just pointed out, you might get a lot of things dissolved or in solution in a geothermal system. So what I'm specifically curious about is the possible intersection with legacy hydrothermal systems or adjacency to polymetallic deposits, or is there a possible intersection, for example, with sedimentary copper, and where you've got one kind of system, but it's also carrying other things. And then on the same kind of trajectory, uranium is very, very mobile in redox interactions in basins throughout the western U.S. Is there any intersection of elevated lithium that's also coming out in conjunction with uranium? I know there's some in Arizona where the high lithium concentrations are associated with high uranium, but I don't know about anywhere else.
I can speak about the closed basin brines with respect to that, and uranium is elevated in I've done some work looking at that actually. Uranium, there are other elements. So Madeline had kind of a nice list for the oil field low temperature brines she was talking about, but there are elevated concentrations of a lot of other metals. One of them is, well, it's a metalloid, it's arsenic. So some of the environmental geochemistry work that we've done around these brines shows, hundreds of parts per million arsenic. And so that is probably coming from the oxidation of sulfides. And this is with respect to the Salar de Atacama and other brines in South America. You would expect that because you have sulfide minerals that are within the big volcanic arc that exists there in the Andean plateau. And so I think that topic is highly underexplored from a closed basin lithium brine perspective.
At the Salton Sea back about 20 years ago, Cal Energy did put into place a zinc recovery facility. It it was abandoned after a couple of years just due to economics. But I think there's a resource there. The companies that are currently looking at lithium recovery are also considering, in addition to zinc, manganese. And one of the plays in Europe are the old Cornish tin granites. And so they have high lithium waters, and they're also very much associated with some of these old metal-bearing intrusions. So I think that there's definitely room for looking at ancient systems that have lithium and other metals associated with them.
Jen, would you like to comment?
Sure. I just want to address Doug's question about copper, uranium, and lithium in the Colorado Plateau, where we've been working. And I would say the highest lithium, or what's being explored right now, is within shales within the paradox formation evaporites. And those black shales could be the source of lithium. We've analyzed them, and they are elevated in lithium. They also could be a source of copper. But for the majority of the copper deposits, like in the Lisbon Valley, it's really more of a shallower source. And that's because we find that the copper is transported more in oxic groundwater than the deeper anoxic groundwater that is the source of the lithium. And the same thing for the uranium. So it's being trapped on reduced minerals, but it tends to have a shallower source than the lithium.
My name is Rita. Sorry. Okay, so the question I have to the panelists has to do with the recharge. So for the different sources of the brine, the lithium, do we have some sort of forecast for how long it's going to be? What's the potential for recharge for those different sources? Thank you.
I can speak to the closed basin lithium brines. So that question around, I think what you're getting at is sustainability. And we did publish on this for the Silver Peak or Clayton Valley deposit. And it really, the short answer is it depends a lot on each basin. And so when I talked about recharge into these basins at the watershed scale, it's important because if you're not recharging with meteoric water, meaning, water that falls from the sky in some way, that infiltrates and it runs off, various hydrologic pathways. But that process and bringing more water into the system is critical because it's linked to the resource, right? So like Scott said, the brine is composed of water plus solutes. So you have to continue to have water. And we are working on this problem and linking this to geologic time and climate change, droughts, mega droughts. Those things do matter, and the long-term climate pattern is really important to understand so that you can assess what your impacts are, your mining impacts, because if you don't know what's happening as the baseline by natural processes, you don't have an idea of what you can extract sustainably.
Just adding on to that for the geothermal context, in addition to meteoric recharge, obviously there's reinjection of the geothermal fluids back underground. For the Salton Sea field, it's a flash plant, so that means you're losing about 20% of the total mass that you produce from your production wells to the atmosphere and the cooling towers. So over time, there is going to be a decrease in reservoir pressure that's going to affect the productivity of the wells and also could result in some surface subsidence.
I would basically say it's very similar for the oil and gas brine. So most of the water, the wastewater is re-injected. That's currently for the bromide industry. That's what they are doing currently. So yeah, most of that water would go back into the subsurface. And as far as if you're talking about if you would create more lithium, that's probably on a much longer geologic timescale.
Madeline, following up on your presentation, when you shared your data on the shale formations broadly defined, you pointed out that only the Marcellus shale has significant amounts of lithium. Can you expand a little bit on why you think that is the case and whether there's lessons there for subsurface lithium deposits more generally?
That I'm not sure I have a great answer for. The Marcellus itself does have a decent amount of lithium in it. And so, I mean, that would be an easy thing to test as far as looking at different rocks, similar type reservoir rocks. And it's also under the, right conditions of, say, thermal maturity, temperature, et cetera, where it's basically being put into the fluid. I think that most other shales just aren't high lithium. And unlike the other reservoir rocks in the conventional settings where you're actually getting fluid flow from other reservoirs, you're not necessarily getting that into the shales.
Doug.
I'm curious about, has there been much work, I'm thinking probably lab work, that goes in the direction of reaction rates? So if you're extracting lithium out of a basin and then putting water back in the subsurface, what is the reaction rate that will then start driving more lithium back into solution? Is that an active research topic? Is it a potential research topic?
I'll give a very quick answer for brines. In many cases where the source of the lithium is not where it's currently pooled, so that wouldn't necessarily apply to those settings. So
I guess for a geothermal setting, your reaction rates are going to be faster. However, it really depends on the mineral that the lithium is incorporated in and how much it wants to give up that mineral. Okay, so we're currently doing some experimental lab work to ascertain the reactivity of lithium-bearing chlorite. This is with folks at University of North Carolina, Charlotte. It's funded by DOE.
Yeah, and similar for the closed basin lithium brines, we have done some work doing experimental leaching of potential source rocks, so volcanic rocks, the clays. This was a study done in Clayton Valley, and we're actively working on this for ignimbrites for South America. And the lithium isotopes are extremely important to use as a tool for this in all settings. So high temperature, low temperature, the salar brines, which I guess could also be considered low temperature in terms of geochemistry, how we define that. But yes, it's active, but it could be a lot more active.
Should mention one more thing. Right now with lithium isotopes, there's kind of a temperature gap for where oil and gas brines tend to be. And I do have my colleague Andy Masterson is currently doing experiments, basically trying to constrain the lithium isotopes for that temperature range, which could help constrain this whole process.
We are at time, but I did want to invite our three panelists and then our earlier presenters if they want to share any last minute thoughts or words of wisdoms or greatest challenge and opportunity before we wrap up. And maybe we can, it's unfair because I didn't give you any heads up. So we'll start with Jennifer because she has had the most time to digest.
Sure, this might seem like a random point, but I wanted to follow up on Madeline's great presentation where she showed that in places like the Smackover H2S is such a good indicator of lithium brines. I just wanted to make the point that there are H2S systems in sedimentary basins that are biological in origin. And that's because these sedimentary basins, the H2S comes from sulfate evaporite minerals that either gets created by high temperature, which could also relate to enrichment in lithium. But low temperature biological processes tend to be shallow and don't enrich brines and lithium.
And this is actually why I really like Leanne's way that she's describing, the low temperature versus high temperature geothermal. So it's a succinct way to say that process would only be relevant for the low temperature geothermal systems, which are high temperature brines, oil and gas brines.
Okay, thanks. I just wanted to mention that I think bringing this team together, all of the people that are here, and trying to advance how we think about direct lithium extraction and the chemical engineering that goes into that. There's a lot of parallels to the natural system and the geochemistry and the processes, and there's a lot of parallels there that I think would be really good to start to explore further.
I guess one of the things is that the group has highlighted is just the variability and heterogeneity of these systems. And so that's going to be a challenge for DLE as well, because it's like it has to work for more than just one brine composition. It's got to work for a variety of brines.
So on that note, I did want to thank all three of our presenters for the second session on domestic resources and our two introductory presentations today. We're going to take a short break, and I think we resume again at 1:30 p.m. Eastern Time. So let's thank our speakers one last time.
Sitting outside for
One. So we heard this morning two excellent series of talks and discussion of an overview of the different geologic environments of lithium brines, their association with lithium sources, and the opportunities and challenges with extracting the lithium and the resource sustainability. So it's a real pleasure to introduce this next session, which is going to focus on the methods, environmental impact, and the economics of mineral extraction from brines. I do have a couple of reminders that you can, to the audience, you can submit questions to the panelists on our webpage in live stream. Look for the Slido box underneath the live stream video. And then to those who are here or online, when you do have a question, you speak, please say your first name and you know to avoid acronyms. So our first speaker is Tom Lagrasso. He's the director of the Critical Minerals Institute. Welcome.
Thank you very much for this opportunity. I want to provide an overview of the various technologies needed to extract lithium from these sources that we've talked about today. Thank the other speakers for laying out the variety of different sources, the different chemistries, and some of the attributes of those sources, high temperature, low temperature, because all of that comes into play when we evaluate technologies that can be used to extract lithium. I am at the Ames National Laboratory. We manage the Critical Mineral Hub, and I just wanted to give a little context to understand the direction that I come from, and that is that CMI develops technologies as part of an innovation pipeline to be able to address the technical challenges associated with chains that are necessary for clean energy technologies, and most importantly, to de-risk those technologies, have a pathway to commercialization. We do early stage research, so our three focus areas are to enhance and diversify supply. Obviously, that's the topic for today, but we also consider developing substitutes and applying circular economy principles to the recovery and production of materials that contain critical elements. We are a public-private consortium of 9 national laboratories, 20 universities, and 36 industry partners working across the various stages of the supply chain. All right, we've heard a lot of different attributes of these sources, and I guess I'm happy to say that there are a number of technologies that can be utilized to extract lithium. I've shown 5 here. These are kind of the leading sources of extraction technologies: absorption, ion exchange, solvent extraction, membrane extraction, and electrochemical. Each of these have its own positives and negatives, and a lot of times the choice of which of these technologies to utilize comes back to what's the source. Not just what is the lithium chemistry, but what's the other chemistry. Shown in these illustrations, we have potassium and calcium and chlorine and sodium, which is common to almost every source. So obviously we want to be selective. We only really want to grab the lithium and leave everything else behind. But there are other elements in these streams, in these feedstocks, and we've heard about them: manganese, zinc. Some are perhaps valuable. You can get value out of them. Some are deleterious, and so we have to choose our technologies accordingly. To illustrate that is dominant here, we can look at how these technologies are being actually deployed. Here is kind of the stage of development of these technologies as they apply to direct lithium extraction for various types of sources. But on the left, it goes from lab scale to piloting to demo and to commercial. And across the bottom are the 5 leading technologies. And you can see that various companies are at various stages, both public as well as private investments in these technologies. What is apparent from this grouping is that absorption and ion exchange typically show the greatest applicability to these dilute sources that are associated with brine. I'm going to just choose this one example as an illustration of kind of some of the factors that come into play. And this is lithium extraction and conversion from geothermal brine. This was a part of a GTO study. The report was put, but it's illustrative without getting into all the details of an actual. But basically the brine comes in and one has to, first of all, think about silica removal or silica management for that matter, because it's not just removal from the stream. It's what do you do with it once you have it separated. And so you think about byproducts, colloidal silica or iron compounds. Last thing you want to do is obviously create an iron silicate that needs to be disposed of. The key there, next step in the center is the improved lithium sorbents. This would be to develop directly out of a chloride solution that concentrate concentrated and then converted into a refined product. That could be lithium hydroxide or lithium carbonate, depending on what downstream activity you're going to field the offtake product will be sold into. In addition to extracting the lithium, you are left with zinc and manganese, and you can go through the precipitation process. We heard earlier that zinc was a pilot plant was developed and then ultimately put aside due to other factors like economics. But now, yeah, we have the valorization of these other materials that are contained in the stream. And then finally, obviously the end product needs to be injected back into the well. Potentially there could be potassium recovery if that's viable. So CMI has worked on sorbents. We felt that the sorbent technology had the most versatility and broad applicability. And we've developed new sorbents that are based on lithium double hydroxide. These have proved to be very effective, very selective in pulling lithium away or out of solution and leaving the sodium and potassium behind. They were developed really to focus on geothermal brines, but we have also found them to be very applicable to the low temperature brines, as well as oil and gas production or oil and gas produced waters. Generally, sorbents are targeted for low concentrations, and we can recover over 91% of the lithium chloride from geothermal brines. That produces a leachate that ultimately needs to be concentrated. We've combined the sorbent technology with forward osmosis membrane technology that concentrates it further from a 3% lithium chloride solution to about 20%. And from there, then we can go ahead and use the lithium carbonate or take it even further into lithium hydroxide production. One of the important aspects to developing technology like this is to understand the environmental impacts. We are replacing the technology, or we want to compare this technology versus others. And so we've done quite a bit. It's kind of part of CMI to understand both the techno-economic and the life cycle analysis aspects. And so, if we produce lithium carbonate from these geothermal brines using sorption and forward osmosis, we find from these analyses that the carbon footprint is 34% lower than production from salt flats and 26% lower than from hard rock mining of the mineral spodumene. Likewise, lithium hydroxide can also see some reductions, not as broad, but certainly on the greenhouse gas emissions. We believe this technology achieves 48% reduction. So when it comes to kind of what are our challenges, for any of these 5 technologies that I listed, it's really improved selectivity. We want to be able to get the lithium, get it quick, the lowest number of stages, and certain technologies are better at that, more efficient. But further R&D investments in efficient extractions, concentrations, and purifications are needed. Oh, I have them all out of order. Sorry. Okay. Well, we need to integrate the DLE process from brines to batteries, and industries have demonstrated individually in several steps. Water management, we've heard this before, so thank you earlier speakers for introducing this issue. Water management is huge. We have to have access to clean water for the delithiation process at the site, and hence water consumption is a great concern. Sustainability of direct lithium extraction over conventional lithium carbonate, lithium hydroxide production methods. We've done some on our sorbent development, but I think we do need to understand if we're going to bring in a solvent extraction circuit, are we gaining anything? What are we gaining, and to what degree, perhaps over our existing production methods? We can do that through life cycle assessments. We have to understand waste stream generations and any public health effects. I think there's, okay. Finally, co-valorization. There's lots of byproducts, but lots of potential critical materials, as Scott pointed out. What can we valorize? And the opposite of this is which are the deleterious elements we have to deal with. And ultimately, to integrate any of these processes, pre-pilot scale demonstrations are needed, whether they're new absorbents or ion exchange methods. So with that, I think that's it. Happy to answer questions.
Great. Thank you, Tom. We have a few minutes for questions, about 3. So if you want to stay at the podium. Yeah, I'm going to start with one that's online. You've spoken a bit to how these technologies can be applied to the various lithium sources of brines. But could you say any more about that if you'd like, or are there certain deposits where they just probably not very appropriate?
Well, there are many factors that come into play to determine whether a technology is going to be appropriate. The sorbents that we've developed in CMI certainly are low temperature sorbents. They are being tested for geothermal brines, but a lot of that has to do with thermal degradation that occurs over time and whether or not that sorbent technology will be applicable. So I think one has to evaluate the appropriateness of any given technology in the context of the source, the impurities, and the production parameters such as temperature.
Leanne?
Oh, did it again. So I'm really curious, you had on one of your slides a 91% reduction in environmental impacts compared to salar brines. And I'm wondering sort of, well, one, is that information public or in the studies? And so one, what environmental impacts does that include and at what scale?
So the studies have been published, and we can get those circulated, the citations. Generally, the life cycle analysis impact factors are about 10 to 12 that are utilized. Boy, don't have a list in my head,
That's
but
okay.
greenhouse gas emission, eutrophication, but there's, it's a standard sort of life cycle analysis.
Okay. Got it.
Yeah. Done at scale. So we try to do that as best we can. Obviously, we're developing early stage technology, and we can compare it to production to technology that is at scale commercial production. But our production, we have to make assumptions about what that might scale. And so we do have to take that into account.
Yeah. Okay, thank you.
We only have time for one more questions, but they're popping in like crazy. So I think I'll ask you, where does the norm, radium and uranium, et cetera, end up in the process?
Yeah, I don't have an answer for that. I think the work that's been done so far has not fully addressed that for the sources that we've looked at. Yeah, I don't recall any of the project team's research results addressing the rad materials.
Thank you again. And if there's time later, we can have a discussion of some of these other questions. All right, our next speaker is Sophie Parker, and she is the Director of Science for Climate and Land Use in the California.
All right, good afternoon, everyone. I think we have reached critical post-lunch sleepiness, so I will try to keep us on task here. My name is Sophie. I'm from the Nature Conservancy. I'm here to represent biodiversity conservation and planning and talk about the potential impacts of proposed lithium extraction on those things in the contiguous United States. And everything I'm going to present today is based on 3 different studies, 2 reports, 1 peer-reviewed journal article. They're scienceforconservation.org. And this was the effort of several scientists at the Nature Conservancy, both within my chapter in California and in 9 other chapters across the US. So for some context here, we're in the middle of this massive energy transition, and thinking about how to address that informs why the Nature Conservancy is involved in this topic. Whenever there's any big change that's going to occur, there's the potential for environmental impacts. And so that's why we care. When there is uncertainty on a topic, when there are things that we don't know, that uncertainty presents risk. And so as far as thinking about how could lithium extraction as an activity affect biodiversity in the United States, our first task was to try and reduce that level of uncertainty. So the environmental impacts of lithium extraction can depend on several factors. We have extraction method, and that can be, as we've talked about, evaporative concentration or direct lithium extraction. We have the different technologies that could be used that Tom was just highlighting. We have the scale of production. How large is this extraction site? And then what I'm going to focus on today are specific ecological conditions, and there are also hydrological conditions that can impact how much extraction could impact the environment. So there are many potential pathways for environmental impacts due to lithium. And here's a conceptual model to begin to think about those. So over on the left, you have the blue box and the different technologies for extraction of brines. And then you can follow those black arrows, which lead to different potential environmental impacts. Wherever there's industry or development, you have the potential for disturbance of soils and vegetation. You have the potential for pollution of air and water, and you have the potential for consumption of fresh water. And then if you continue to follow those black arrows, you can see how those environmental impacts could lead to impacts on specific groups of organisms, plants, terrestrial organisms, and aquatic organisms. And critically, there are also ecological impacts of how those organisms interact with each other that we need to consider. So by the complexity of the number of black arrows on this diagram, you can see that this is already a very complex topic. So in order to try to dig into this, what we did was a simple overlay analysis. So we began by looking at where there are brine resources in the United States, and we talked to experts and we did internet-based searches to find where there's industry interest in developing those resources. We found that there were locations for 72 proposed lithium projects across the United States, and 57 of them involved brines. Now, of course, there are probably a lot more now, as this study was done in 2022. If we zoom in a bit here, just looking at California and Nevada, each of those potential project sites is shown in the red on top of this pink overlay here. And the centroid of each project is shown with the darker red circle. And zooming in a bit finer here for a specific site, here's Panamint Valley in the California desert. The actual mine claim is shown by the solid line, and we added a 2-mile buffer around each site to capture the fact that there are some impacts that could be felt beyond the mine claim itself. Imagine fugitive dust, or imagine the drawdown of groundwater that extends beyond the claim boundary. So then now that we have this information about each site, what we did is to layer on top of that existing data sets related to biodiversity conservation. These come in different categories. We have species and natural communities, we have conservation value, habitat, and land management designations. And what I'm showing you here is a very truncated list of the total number of data sets that we use. The complete table is about 10 pages long. But the ones that I'm going to talk about today and show you maps of include citizen science species occurrence data, the Nature Conservancy's data layers, desert tortoise habitat, and national parks. So here's what these look like at our example project site. Now, if you can see in this map, for species and natural communities category, the citizen science species occurrence data are shown by the orange stipple across this site. So this is an example of people going into the field, capturing information about the organisms that they find on the ground and entering it into a publicly accessible citizen science database like iNaturalist or eBird. The Nature Conservancy has developed on an ecoregional basis a number of different data sets that show how we can focus on protecting biodiversity across the United States and around the world. These polygons are based on vegetation types, intactness of habitat, and the potential to support biodiversity. So that's what that looks like at this project site. Additionally, we have what are called recognized biodiversity data layers, and you can see how those data differ from the previous layer in terms of where they're showing up at this project site. There are mapped habitat polygons for special status species, in this case, the desert tortoise, which is federally listed as threatened, that occur within several of these lithium extraction sites. You can see the little orange square near the top of the claim area. Additionally, there's some additional areas within this project boundary that are mapped as desert tortoise habitat. And importantly, there are land management designations, particularly on public lands, that can impact how those lands are managed for biodiversity. There are some lands that have a very high level of management, such as wilderness and national parks, and other lands that have more of a public use mandate. So here you can see the green portion of the map is National Park Service land, in this case, Death Valley National Park. It's peeking in to the 2-mile context for this project site. So those are some examples in a mapped form. We can also look at these data in a tabular form. In this case, in California, we have the species that are federally and state listed on the left-hand side of the table. And on the right, we have where they're recorded for 15 different lithium extraction sites, potential lithium extraction sites. The ones that are grayed out are ones that don't have to do with brines. The ones that are in white are ones that contain brines. And what you can see from this is that there are many cases where there are listed species that have been mapped within the sites for proposed lithium extraction. We can look at the same sorts of data for conservation value, habitat, and management. And our major findings here are that hundreds of species have been observed within our 57 sites for lithium extraction from brine. 204 are rare, special status, and or state tracked species. 3 are federally endangered. 1 is a federally threatened species. 51 are state listed as endangered, threatened, or special status. And the rest of the 204 are listed by the International Union for the Conservation of Nature as near threatened, vulnerable, or endangered species. And there is taxonomic bias within the field of data collection. Birds are the most recorded taxonomic group and appeared across the broadest geographic range of sites. And wetlands were the most common mapped habitat type. So in conclusion, I have some thoughts, recommendations, and points that hopefully generate discussion here. Potential environmental impacts of lithium extraction from brine vary from site to site. It's not the same at every site. More field-based studies at proposed extraction sites are needed to understand the biology and the hydrology well enough to quantify those impacts. Our study is just a very high-level basic overlay analysis. We need more data. All methods of extraction from brine could impact wetlands, freshwater and groundwater dependent species and ecosystems. Those groundwater impacts are site-specific, complex, and where groundwater is very old and is not being replenished quickly, those impacts could be irreparable. So think about springs in the desert. If those springs dry up, there's no place for organisms to go and hang out while they wait for the water to come back. Cumulative impacts analyses focused on wetlands are necessary. There are many places in the United States where there are migratory species that use not just one wetland, but multiple wetland systems. And so being able to understand the potential impacts across the region and even at a continental scale is important. Here's this life cycle analyses. Again, I'm using it in a different way here. Thinking about production, life cycle analyses are necessary for understanding impacts, not just extraction, but the full suite of different activities that occur with production of lithium. It's important to understand all of them. And finally, with enough information, employing a smart from the start approach is possible. That means that we have the ability, because we have so many different places where this extraction activity could occur, we can start by focusing on places that potentially have the lowest impacts first. And I'll stop there and can take any questions.
Thank you. We have time for 2 or 3 questions, so if you'd stay at the podium, please. I'll start with one that we have from online. So you've spoken to the very large differences in potential environmental, including biodiversity impacts among sites. So what would you think would be the greatest uncertainties in determining these impacts of brine extraction at a particular location? Maybe this one from the short and longer term perspective.
There are many places that have not been well botanized, where field surveys simply have not been done. And so collecting more information on the ground is truly necessary in order to understand impacts for species. We need to be able to fill up our databases with information in order to make predictions about what could happen to species. We may have a sense of where a species is located in a broader region, but when it comes down to site specificity, that on-the-ground information is absolutely critical.
And then how did you determine the 2-mile buffer around the Panamint Valley project?
Yes, that's an art, isn't it? It's somewhat arbitrary. There's no perfect way to make a buffer, and this is one that we commonly use in conservation planning.
Leanne?
Thanks, Sophie. I was curious if you could just comment briefly about the criteria used to identify 57 brine projects.
Yes. So what we did is we found all of the places that we could across the United States where there was an expressed interest in developing lithium resources. And some of those were hard rock and clay, and some of those had a brine component. And so I just took the list and took off the ones that were the hard rock and clay, and the remainder were those 57. I think there are far more than that. Those are the ones that we were able to find with our research at that time.
Okay, so yeah, I guess I'm wondering what sort of verification process, or is it just if you found information that maybe like a junior exploration company was interested in brine, but maybe hadn't actually found brine?
It runs the gamut.
Okay.
Yeah, some of these are, it's from claims databases at the state level. It's from websites from particular extraction companies in the mining industry. It's from your own feedback that we talked to you and other experts about where they knew there was industry interest. So it's a variety of different sources.
Okay, and can I do a follow? No. Okay, thanks. Okay.
Oh, we have time for one more question. I'd like to pick up Alex's question. That's okay.
Hi, thanks for a great presentation. To what extent have you and other environmental groups been working with state and federal regulators to try to figure out best practices for permitting? I mean, presumably a lot more work needs to be done since it's at an early stage, but you can talk about that. That'd be great.
Yes, all the time. So we do our work at the Nature Conservancy in collaboration with whomever will work with us, with industry, with the regulatory agencies, with academic scientists. We're in constant contact and good communication with Bureau of Land Management, National Park Service, Fish and Wildlife, all of those agencies. So it's a big part of what we do. Yeah.
Thank you again, Sophie.
Thank you.
Oh. Protocol changes. So I want to remind the audience that you can submit questions to the panelists on our website, webpage live stream. Look for the Slido box underneath the live stream video. Okay, so our final speaker is Simon, well, the final of this session, Simon Jowett. Simon is a tenured director of the Ralph J. Roberts Center for Research in Economic Geology and the Arthur Brandt Chair of Exploration Geology at the University of Nevada, Reno. Welcome.
Thank you. Yeah, I'm going to kind of wrap up this session by talking a bit about the economics of brine resources and continuing on a kind of theme that Sophie started by talking about uncertainty in the brine and specifically the lithium from brine or lithium sector in general. We've heard already that a number of different minerals and metals can be extracted from brines. These include boron, sodium carbonate. I've got a list on there, but basically, as we've heard a lot about today, the majority of current R&D is focused on lithium, and that's likely to see the largest growth over the next few decades with significant amount of investment taking place in this area already. And so I am going to be focusing on lithium mineral economics, talking a bit about supply and demand balance, price variations, and the likely impact this is going to have on lithium brine project development. We know that the lithium market is complex. I think Scott touched on that a little bit earlier. And the majority of lithium that's produced is actually sold via offtake agreements. So lithium producers have direct agreements with a lithium user, like a battery EV manufacturer and so on, rather than on the open market. And that appears to provide some security for individual operators against volatile lithium prices. If you've looked at the lithium price over the last couple of years, you know it's kind of going all over the place. The question is, this is hedging against that price volatility. It's providing a bit of reassurance, but the question is how robust. And what we need to think about, we're talking about all these potential developments in terms of lithium extraction. What we need to think about is the timing of that demand increase that we're seeing for lithium versus supply increase. Are these matched or are they offset? And what implications does that have for essentially the lithium market and the stability of lithium producers? We know that drivers of demand increases in lithium-ion battery production, but there's also policy drivers. If you look at the change in tax breaks for electric vehicles, that drove demand up for lithium to end 2022, and then we had a lithium price crash because of the change in demand for lithium as a result of those changes in policy. So this time, and the other thing to think about in all of this is the timescales of permitting and development versus demand increases. So there's a whole load of uncertainty on this balance of supply and demand that we need to think about in terms of its impact on the development of brine projects, specifically for lithium in this case, but you could apply this to any kind of brine extraction project. One example is, in terms of offtakes, we've seen offtakes in agreements from California, from the Salton Sea projects. There's multiple offtake agreements on clay and brine deposits in Nevada. One example of this is, I think actually Scott mentioned Compass Minerals trying to derive lithium as a byproduct of magnesium chloride production from the Great Salt Lake. They had an offtake agreement in place, but basically that project was scrapped in 2024 as a result of technical challenges, which means that lithium is not going to be produced. So this indicates that even with these offtake agreements, which might provide a bit of reassurance, price volatility, technical challenges can cause significant issues. And there's other factors like California has actually brought in a tax on lithium carbonate production, $400 to $800 per ton of lithium carbonate production from 2022 onwards. That scales on production. And also that, if you compare, for example, California to Nevada, where we don't have such a tax, that may actually create a bit of a difference in terms of where you might actually see brine projects developing versus brine projects having more challenging economics. This is what's happened in the lithium price from 2017 through to more or less the present day. You can see this is essentially a spot price for lithium. I haven't got the actual kind of values on there, but what I've done is I've normalized the price to 10th of May 2017. So in other words, that kind of getting up to 5 means that lithium between, say, 2022, mid-2022 and 2017 went up 5 times. We're back down to approximately the same level as we are in 2017. The thing to think about here is that this volatility we're seeing over the last couple of years, we need to compare to the time we need to actually develop a given project. Lithium extraction projects may take 5 to 10 years. This graph goes from 2017 through to 2024. So this is probably on the order of timescale the development of a lithium brine extraction project. The question is, how can lithium brine extraction projects or any brine extraction projects deal with this type of volatility and uncertainty? There's a bit of some interesting data on here. What we've got is essentially a price variations shown in that kind of yellow color, lithium production, lithium reserves from the USGS. So we can see that lithium reserves and production are actually increasing kind of systematically over the time. And what we've got there is a ratio, and that ratio just shows the ratio of essentially reserves to production, or in other words, how much annual production divided by total estimated reserves globally. And that kind of indicates that the amount of lithium we've got in the ground relative to the amount we're producing is somewhat decreasing, at least in some estimates. So that means that we may have a bit of a problem in terms of lithium supply, but there are an awful lot of other considerations to think about that I'll kind of summarize. If we think about demand into the future, estimates suggest that we might have by 2030, we might need 400,000 metric tons of lithium carbonate equivalent, or about 80,000 metric tons of lithium metal demand here in the US, mainly for electric vehicle batteries. That's equivalent to about 700 gigawatt per hour lithium ion battery capacity. Currently, as other speakers have shown, we produce about 5,000 metric tons of lithium carbonate, or about 1,000 metric tons of lithium metal, almost all from a Silver Peak brine operation in Nevada. But the thing to think about is that we're likely to see a significant ramp up of lithium production in the US. If you look at Nevada alone, we're going to produce, hopefully, maybe about 136,000 lithium carbonate equivalent tons per year, mainly from non-brine sources. Thacker Pass, Rhyolite Ridge. Silver Peak is actually expanding its operations and trying to double production. We estimate we're going to see a significant amount of potential production from the Salton Sea, and globally lithium production capacity continues to expand. The question is, how is all this going to balance out? If we get everything coming on stream at once, like direct lithium extraction from oil field brines, from geothermal brines, expansion of other brine operations, and the addition of clays, is this actually going to mean that in the short term, we're going to have an excess of lithium, which could create challenging economics for individual lithium producers? But in the long term, if we actually have undersupply, what's this balance going to be, and how is this balance of supply and demand going to play itself out? And this is just looking, this is a similar diagram to that Leanne showed earlier. This is just looking at lithium production globally. We've got hard rock brine and mixed production compared with the real lithium price normalized for inflation to $1998. We know that this is predominantly from a traditional continental brines and hard rock production. There's minimal contribution from clays, geothermal, and oil field brines. So the question is, is the expected increase in demand going to match this expected increase in supply we're going to see from all of these sources that aren't yet on this graph? We know that some producers have delayed or scrapped plans for lithium production, and we know that maybe it's also easier for hard rock producers to ramp up production. If we look at a traditional evaporative brine, it takes about 2 years for that brine to go through the process of lithium production. And that means that any brine operators who were starting to ramp up production 2 years ago may only start to see that lithium increase happen around now. And this is just looking at some of the, I'm not going to go into the details here, but if anybody wants this information, obviously the recording is here. But this just looks at one state alone in the US, Nevada. Obviously, I'm biased coming from there. But the fact is that if you look at the overall total of reserves and resources, you know, we're talking getting on for 118 million tons of contained lithium carbonate, mainly in clays, but there's also some potential brine projects there, as well as the currently producing Silver Peak brine operation, which is going to be doubling production in the near future. This is just one state in the US, a state that has a lot of lithium. There's an awful lot of other lithium likely to come on stream, which may challenge the economics of these brines that we're talking about today and these brine projects. And we need to understand this type of uncertainty, as well as the environmental impact uncertainty that Sophie mentioned in the previous talk. And this is just one example. Again, this is the Sparks Gigafactory in Nevada. Tesla Panasonic has a capacity of 35 gigawatt hours of cell production per year, about 500,000 Teslas. If you do some calculations and assume they're producing what's called NMC 811 batteries, that just means the cathode in those batteries contains 80% nickel, 10% manganese and 10% cobalt. This factory alone needs about 4,000 tons of lithium, an awful lot of cobalt, nickel, manganese, and graphite. Global nickel production, as an example, I'll explain why I'm talking about nickel shortly, is estimated in 2023 to be 3.6 million tons. This factory alone consumes about getting close to 1% of global nickel production. And if we go to nickel and more nickel enriched cathodes, you know, that means that these factories are likely to consume even more nickel. And there's 300 of these either planned, developed, or completed underway globally. So this is the kind of demand side of things. But the other thing we need to think about, because we're talking about lithium-ion batteries as a driver for lithium demand, it's not just the lithium that comes into play here. It's all the other things that we need to put into these batteries, and that will potentially affect lithium demand. If you don't have the nickel or the graphite, or you have an excess of these things, then all of a sudden your lithium-ion battery demand and your lithium demand may be affected by these other supply chains. So there's a lot of uncertainty to think about here. We don't know the timescale and effectiveness of direct lithium extraction yet. We talk a lot about clay sources of lithium, sedimentary lithium, but as yet, there's not been any successful development of this on an industrial scale. So we wait to see what happens at Thacker Pass and Rhyolite Ridge and so on. We need to think about the timescales of mining and brine operations. If you look at the IEA data from 2021 and Richard Shoddy's data from Australia, you know, we might go for 4 years from discovery to extraction for lithium in Australia, pegmatites, 7 years in South America, but we don't really know about brine operations here, how long they will take to come on stream from going from essentially a discovery to production. Environmental, social, governmental challenges are huge for all extractive industries, especially mining. There's other developments of grid scale storage, which could provide opportunities for alternatives to lithium. And we need to think about, again, this balance of supply and demand and price volatility. And that's especially true of lithium. Lithium is a small sector. If we look at volatility in larger sectors like nickel, this is just an example of the nickel price over the last 2 years or so, going from a peak downhill. Why do we care about this? Because nickel is a major part of the lithium-ion battery supply chain. And the fact is nickel is currently in oversupply, and it's going to be an oversupply to the end of the decade. What does that mean? You actually look around at nickel mining operations. BHP's Nickel West has been written down by $2.5 billion, and nickel at current prices means that only 35% of global nickel production is likely to be profitable. We don't know these things for lithium operations yet. We don't know what the break even is for a typical direct lithium extraction operation from a geothermal brine and things like this. This all leads into the uncertainty over the lithium sector. So the question is, if direct lithium extraction works perfectly, geothermal brines for oil field brines, lithium clay processing works fine, are we likely to have an oversupply period, a short-term period of oversupply, and then maybe undersupply as the lithium demand overtakes that lithium supply? Pricing impacts are huge. There's a few days ago, Century Lithium's Clayton Valley, a direct lithium extraction brine project, released a feasibility study using a long-term price of $24,000 for lithium carbonate. The current price is about $15,000, so their shares actually fell as a result of that step towards developing a brine operation. Discovery is one thing, but capital investment, especially for small companies, is a real challenge. And we also need to think about this on a global basis. We're not the only country producing lithium. We're not the only country looking to produce more lithium. There is a global market for all of this, and we need to think about global production from friendly countries, unfriendly countries, and where our lithium sector is actually going to get this lithium from in the future. We need to understand all of these uncertainties to work out what the likely impacts are on the success or failure of individual lithium projects or parts of the lithium sector. Just kind of wrapping up, the small scale of this sector combined with the timing of supply and demand changes that we still don't really know and is affected significantly by policy can lead to significant price volatility. It's unlikely that even offtake agreements is going to reduce this volatility a huge amount. Policy developments and changes are huge in this area. We need to consider the interplay between lithium and other metal supply chains as well. And we need to understand changes and uncertainties to ensure that the lithium brine industry is prepared to weather this volatility. Otherwise, projects may fail, and that means in the long term, we may actually end up with undersupply if some of these projects don't make it through some of these volatile phases we're seeing already. We need to think about what is a break-even point of an individual project compared to actual likely lithium prices for salars, continental brines, oil field brines, geothermal brines, and then the impact of hard rock and sedimentary lithium sources coming on stream. And as mentioned earlier, critical metals may not always be critical. There's no problem with a single point of failure here necessarily for lithium, and we know that import reliance can decrease rapidly for some critical metals once we get secure supplies on stream. And one example of that is tellurium, where supply is actually, import reliance has decreased from 75% to 25% in 1 year as a result of developments in that sector. Lithium is a bigger sector than tellurium, but the fact is if we get multiple sources come on at once, that could lead to challenging economics for a number of domestic projects. And that's about it. I'll happily answer any questions. I know I've thrown a lot of information out there, but the fact is there's a huge amount of uncertainty in the sector that I think we need to understand. Some of these developments are great, but we need to understand whether they're economically viable and what the overall scenario is for the stuff we're talking about today, put in a global context of the lithium sector.
Great. Thank you very much, Simon. So we have just time for 1 or 2 questions. I'm looking to see if yes, please.
Gary Goldberg. Simon, great overview, and especially on the overall economics. How does recycling play into this down the road? Because eventually those Teslas got to go in and get a new battery. What happens to the old battery, and can they recover that lithium and nickel and all the other elements?
One would hope so. Otherwise, kind of all the lithium we're using is one use only, and then we're really in trouble. But I think that there's a number of large developments going on in that area. I mean, we're seeing already recycling kind of facilities tool up using the black mass that's coming off battery production lines. And the other thing is we need to actually think about what type of recycling are we going to do? Are we going to literally recycle, like take one battery and turn it into another battery? Or we're just going to take batteries out of electric vehicles and use them in a different way? Because if you, say, put them as grid scale storage, then all of a sudden the cycling of power means that those batteries could actually have an extended life without actually formally having to recycle them. So repurposing rather than recycling could also have a significant role here to play. But I think that there are a number of positive developments, but that's a crucial thing in all of this, because we can't have this lithium coming out of the ground and being just one use only, then being wasted.
Thank you. I'm afraid we're going to have to move on because we have a 11 minutes break now, and then we'll reconvene precisely at 2:30. Thank you again. Appreciate it.
Yeah. Who knows? Here we go. Okay. By the way, my name's Doug Holland. I'm a member of the CER committee. This next conversation, this next panel is going to be basically focusing on research needs. Now that theme has been underpinning pretty much every one of the presentations earlier. We're going to revisit that, and we're going to try to revisit that in a little bit more depth. I'm not going to ask the speakers to do intros or such, since you've already met them. We'll just get underway in just a second. And a reminder, if you do have for the folks online, if you do have questions, just make sure you click on the Slido link at the bottom and enter them in, and then they'll pop up here so we can get to them. So what I'm going to ask this group to do is to start out 2-3 sentences or that kind of length. Identify what you think are the highest priority research and policy needs. Basically you're looking at the interconnection of technical R&D, but also policy R&D. Where you think the biggest gaps are, the biggest needs. And I'm going to start with Jennifer.
Sure. I wanted to emphasize a point that came up today, which was about the scales and the idea that you not only need lithium within brines, but you also need to produce enough fluids. So I just wanted to reemphasize that I think that we need research in the area of the amount of water that can be produced from these reservoirs, because not every lithium reservoir will have high lithium concentrations. And some of these reservoirs, like we heard about the shales, the unconventional reservoirs, will have low permeability. And it's actually permeability that's varying over the most magnitude, say over 5 orders of magnitude, versus lithium concentration, which has lower variability. And to talk about scales in terms of if we were to scale this up from sedimentary basins or oil fields, we're talking about producing lithium to match global production. And that's really on par with the amount of water that's been produced with oil and gas over the last 100 years. So I think that aspect of scale needs to be an important part of the conversation. And again, permeability and how much fluids can be produced.
Great. Scott.
Yeah, I would just say, first off, that the framework here of brine types and deposits that we've talked about, when I started doing this work, wasn't quite so coherent. So I think that's a major advance. And then, some of the things related to research, in closed basins is pretty easy. Nobody really wants to count reagents or product or monitor water. It's just expensive and not scientifically interesting. But in a closed basin, the only thing that leaves is water by evaporation. And it's a really excellent opportunity to understand the cumulative impacts of things. And then the other, I guess, final comments I would make are sort of related to in situ sort of leaching and, sort of research boreholes and pumping tests and injection and, kind of expensive things that would answer some of the questions about how reactive are the aquifer materials, what types of enhanced production, would work in certain reservoirs. And then, I was really happy to hear about the work that Tom's doing, but I think one of the issues with DLE that we need to understand and where more public research needs to be done is a lot of that research is done with the hopes of licensing technology. So people are going after deposits just because of the technology, and the deposit itself may never pay off. But if you can license the technology, there's an economic advantage. And so it was really nice to hear about Tom's consortium and how they're approaching that.
Great, thanks. Sophie.
I think the main thing that comes up for me is the need for field-based surveys for species. In order to understand impacts, we need to know what's there. And there are many locations that have not been well surveyed, not been botanized at all. No one ever has been on the ground to look at them. There are no records available or very, very few. And there are big taxonomic biases in those records. So being able to get comprehensive data or any data on the ground for what species are present is probably one of the major recommendations that I would make for understanding impacts. And then in addition to that, being able to use those data to conduct some habitat suitability modeling to be able to understand how big of an impact of a total species range would any one particular project site or extraction impact. So if there are some species that their entire range is covered by a project site, there are other species that are very wide-ranging where that's not the case. And so understanding those differences is key. And then additionally, cumulative impacts analysis, as I mentioned during my talk, particularly when it comes to thinking about wildlife that use wetland resources across their range and have multiple stopping points on a migration route, for instance, being able to understand changes that could occur due to lithium extraction and how that could influence their ability to complete their life cycle and complete their migration.
Great, thanks. Leanne.
Yeah, I have two items. One is related to the supply chain. And my recommendation is that we need to think further up the supply chain than we have been. And what that means is exploration and discovery and characterization of the ore deposits. So if we just take lithium in the United States, for example, we really don't understand how much we have, where it is. So I think a lot of focus I've seen has been on the downstream where it's like, okay, are you making a battery? And with respect to other elements, are you making magnets, whatever it is, like sort of that, what are the products coming out? But there's a lot of work that needs to be done before we get there. The second is around water. So we're hearing this water theme a lot, but water resources, use, availability, what are the basin scale? And one thing I like to call a mega watershed is not just looking at individual watersheds, but looking at regions. So, maybe you could think of like the Great Basin, right, as one, the Puna Plateau in South America. So what are the connections between the fresh, the brackish waters and the brines? I think those are the important pieces.
Yeah, thanks. Got three things. One is a lot of these studies have shown the resources are there, but we just don't know if the technology is in place to economically be able to recover the lithium from the different brines. So just seeing will DLE work at a commercial scale. Reiterating what Leanne just said, water is critical for all these things. For the Salton Sea, you're in an area where you have restricted availability of water, and figuring out how to balance the water needs of the community and how it impacts the environment is really important. How you can reuse water and recycle water in different ways. And then the third thing is resource management. There are multiple companies that are going after a single resource in the subsurface, and there may need to be policy changes to ensure that the companies optimally utilize this resource. You have these artificial lease boundaries, but the resource doesn't really see them underground. And so how do you make sure that when you have different companies putting their straw into the same resource, that you're doing utilization in an efficient and optimal way?
Okay, I'll talk about one research need I think is important. I think finding this middle ground between any of these new critical mineral recovery technologies and what sort of real world samples are going to go into that. A lot of these are developed using idealized compositions with lithium in it. And the big question is when you start including, for example, oil and gas brines, when there's oil and gas in there and other organics, when there's other components in there, what is that actually going to do to the lithium or other commodity recovery?
Yeah, Simon.
I think understanding some of the uncertainties around the lithium sector. I mean, I talked a little bit about supply and demand, and Leanne mentioned a little bit briefly there, but just to work out what we have in the ground, what's likely to be needed, and what that kind of relative timing is, because we can talk about all these exciting developments, but the fact is, if a lithium project is never going to be economic, or is only going to be uneconomic under certain circumstances, we need to know what those circumstances are and factor that into actually working out what our domestic supply situation is going to be. And that includes environmental and social challenges, because they're the biggest challenges the minerals industry faces right now, including brine development. And if we don't understand the potential impact of those on lithium supply, then I don't think we have a full picture.
Two items. Thanks, Doug. From a technology standpoint, I think a area for research is improving selectivity. The more we can be selective or target the particular element that we wish to extract from whatever that resource is, for whatever element, the benefits are multifold. One, we get we get a higher efficiency of recovery. So we need less stages, we need less water, we need less land footprint, less capital expense, less operating expense. So reducing the number of steps through more efficient and selective separation processes is clearly a fundamental need. Second point is more technical or technological, and that's we need technologies that have maybe a versatility of application. As we've heard throughout today, the sources are wide and varied. If we can develop technology that can be utilized for multiple different sources, multiple different brines, but hey, if it works and it works on tailings to get the lithium, I mean, that would be great. Those are my 2 points.
Okay, great. And then I'm going to start sort of going backwards, because with all these R&D needs that you identified either earlier in the day or right now, can you compare the needs or the collective needs with that funding landscape? Funding coming from either NSF or from DOE or other agencies. How, without a number, how big is that gap?
So right now I see the gap as being in kind of the mid stage of development. We do really well in discovery science and getting things to lab scale and even maybe bench scale. And to jump right to pilot scale is frankly too big of a jump. I think we need test bed facilities. Department of Energy is beginning to provide some investments in this area. Really, to your point, does the technology work at scale? But to invest tens of millions of dollars in a pilot scale activity before it's really validated at an intermediate somewhere between bench and pilot seems like we're jumping too fast.
Simon.
Difficult question to answer, but I think what we need to do is we need to actually look at the science and research that we're doing and work out what's impactful. I mean, we can all do good science, but what we need is actually impactful science that will specifically change things like advancing direct lithium extraction or understanding more about brine systems so we can actually apply that knowledge and extract things in a more environmentally or sustainable way. So actually thinking about the research we do and working out, or even just looking at the research we've done already and seeing what's impactful and what hasn't been so impactful and learning for that and developing directed funding solutions may be one way forward. It's just a thought.
I work for the U.S. Geological Survey, so we're not a funding agency, so it's a little bit different, nor are we regularly, trying to get funding. But I think it is important to note that a lot of these fundamental questions are things that the USGS is set up to look at on a large scale with teams of assessment geologists and whatnot. So if there are those sort of basic not necessarily technological questions, but these sorts of things that, you know, the information that you need to be able to scale up and build. These are the sorts of things that, you know, the USGS and higher levels within the USGS can organize to get funding to do.
Pat, and then I'm going to switch questions to the next one.
Okay. So I would say that, you know, at the National Lab, we've been fortunate to get DOE funding and California Energy Commission funding for some of the projects we've been doing on this research. I would say one challenge is not necessarily funding, it's data. And some of the companies that are involved in this are very secretive and don't share information. And so being able to build models really depends on having useful information. And I think that's a critical challenge. You can have all the money you want, but if you can't get the information you need, it makes it hard to do a good job.
Okay, and I'm going to switch questions a little bit. You know, Tom mentioned test facilities, test capabilities, pilots and such. And Simon had talked about sort of the gaps between, you know, both the price deck and how that's going up and down, but also the scenario of 1 year having oversupply, the next year having a significant undersupply as the demand curve goes up. Could you talk about how something that like Tom was talking about, an organized test facility, you know, a significant test facility to test lots of brines against lots of DLE technologies, how that might sort of either muddy the waters or accelerate science and learning? I'm just going to start with Leanne.
Yeah, I mean, I think that I would like to point out that lithium brines, for example, we don't know that much about them, right? Like compared to gold, silver, copper. There have been ore deposit models around for those other metals for hundreds of years. So we're trying to accelerate something that we just haven't really been working on for a long time. And I think it's going to take a new approach. It's going to take multi-agencies, multi-universities, researchers coming together in a very big effort. And I don't think I mean, there might be some mud in that water, but that's what we have to do, right? If we want to do this quickly and innovate and accelerate. So that's sort of my vision of how we could get together and, you know, work towards these goals of increasing domestic supply, relying less on foreign supply chain.
And then Sophie, your areas that you talked about are a little bit different. So how could there be a more organized, basically the equivalent of a test facility for the kinds of topics that you were bringing up?
Yeah, thank you. I think that the information that we have about species and natural systems is largely contained in our natural diversity databases at the state level. And those are funded by the states in a variety of different fashions at different levels. There's no unified federal level national biological survey entity. And so the information is really state by state. And then there are a variety of other entities, nonprofit organizations, academic institutions, museums participating in gathering that information. If we had a particular topic that we could organize around and identify the landscapes of interest and have funding to be able to address that, that would probably be beneficial.
And then just to draw on that really quickly, could you talk about how that would and tie into this broader topic that's been brought up a couple of times of community and social understanding or acceptance of the mineral sector more broadly?
Yeah, I think that's a really important point to bring up. And I think there's also, in addition to that, tribal issues related to this topic that I think require serious thought and consideration. A multi-stakeholder, multi-interested group organized around around this topic could be helpful. Folks that represent how do we bring the biological and environmental information to bear, in addition to how do we incorporate that information, the information that already exists, how do we gather more, and then how do we work with communities to make these approaches something that communities are going to be willing to accept and want to support. I think there's a lot of work that needs to be done there.
That's great. Scott, a different kind of question for you. A lot of the talk here has been on how much activity there is. I can't remember if it's 57 or 72 projects in Nevada alone that I think Simon had mentioned. But can you talk about how that this R&D can then also help identify the places to not go, as opposed to the places to go? In other words, there's a technical slice there. There's an economic slice. Can you talk about that a little bit?
Well, I would say for a long time, for example, on Great Salt Lake, there have been 4 different mineral operators sharing a resource and operating simultaneously. And that's a best case scenario, right? You don't have to pump it up. It's floating around at the surface, right? So lift is one thing. The shallower you are, the more accessible things are in terms of energy. And then, I think, the magnesium's a thing, for lithium, and Sophie, everyone's mentioned this, but I think it's important to recognize that it's not just for DLE. It's also interferes with your extraction process in ponds. So the exact same thing. And so I don't know, identifying the challenging chemistries, but I think, honestly, if you looked at the Western US and you thought about it, there would be, what's the brine chemistry? What am I trying to get out of it? And then your immediate next question is, how much water is it going to take and how much water is available, right? Because there are some places where you can't take any water out of the ground at all. I mean, it's a non-starter. And I think that's one of the challenges here is identifying places with available water resources, I think would be a really critical overlay to some of that.
Jennifer, sort of on that same theme.
Yeah, I think back to the water, had a comment about that. It really depends on the system. For these closed basins, we saw that the groundwater is circulating on shorter timescales and that it's part of an active groundwater flow system. Within sedimentary basins, we're talking about producing very old brine with the oil and gas. And in so that case, you'd want to go to a place where there isn't recent meteoric recharge because the lithium will be too low. Maybe there's a water issue with production of lithium at the surface, the extraction of the lithium. And like enhanced oil recovery, they do add near surface water to enhance the pressure within reservoirs once you extract the fluids. But I just wanted to make that point that, that water footprint is very different from oil field brines than it is from closed basins. I also just wanted to return to, in my mind, one of the gaps in basic research needs, which is knowing the lithium sources. So I think you heard today that we often wave our arms about lithium might be coming from volcanic materials or it might be coming from clays, but I think that we really don't know. And that's where a lot of basic science research needs to head, both from the rock and the brine side.
And that's a good segue into one of the questions from online here. The question is, where is the research on reducing the risk of brine exploration? In other words, either funding wells or funding drilling and testing data that then is immediately open source, so it's available. So is there any the research, I guess, that reduces risk of exploration more, fundamentally? This is not just a lithium question. This is pretty much every metal, but it's a good lithium question too.
I'd say a couple things quickly, Doug. One is basin scale geophysics, right? Because if you go down somewhere, you want to know, am I dealing with one aquifer or 5 aquifers, or, how many reservoirs are there? And that's very difficult to do by drilling. It's really great snapshot, aerial geophysics or other things. The other thing I'd like to point out is the state of Nevada now has a brine exploration program, which they permit, and you have an extraction well and I think a reinjection well, and you have to put meters on both of them, and they lower basically, and they're fairly easy to get. And you can do whatever you extract what you need, assess how the aquifer performs, what's in it. And then you basically, if you don't do anything with it, you have to plug it in something like 3 or 6 months and it's done. But they've kind of come up with a way for people to go in, quickly and cheaply and rapidly assess what's there, and then basically seal it up. And then they keep a public database of those activities.
You have another question, Jennifer, or another comment?
I was just going to add to that in terms of reducing uncertainty or risk. I mean, I think we've presented today that there are certain fingerprints that you could look at that would show you, is there a higher or lower probability? Our data is very few and far between with lithium, but also other commodities that might be produced. So helium, hydrogen, things like that. And so some of these deep brine systems may also be places where you could find these other resources. And so not just measuring lithium and major ions, but gases and things that might also be an additional resource.
Which would mean the funding to make sure that all that data is collected too. Okay. I've got a question now for pretty much for everybody or for anybody. We're talking about lithium brines, but the funding sources or the R&D funding sources don't organize necessarily that way. They organize either around other commodities. In the case of the Critical Materials Institute that Tom has responsibility for, it's around an institute, topics within an institute, or it's central. In Madeline's case, it's central to what the USGS is doing. Does that make this easier or harder to try to drive R&D that basically is crossing every one of these boundaries? I'm just curious if anybody has if you can just raise a card so I can just see. Leanne.
I didn't even get my card up, thanks. So I'm just going to speak from my personal sort of long-term experience working around the lithium industry. And where I've learned the most is going multiple times to the sites, doing the field work, interacting with the industry, the people who are doing the work. And that's something that takes time, and you have to gain the trust of companies. But I think that if we could bring together like an industry consortium, like an example is, oil and gas industry has done this. If we could bring together a consortium of the industry people and this is kind of getting to my faceted work group, I think that would help us accelerate and move in the right direction.
With the chance of touting my own institute, I think the consortium model that CMI has been able to deploy actually addresses what you've characterized as kind of the boundaries in between all of these issues, right? So our approach, while we may be focused on developing a sorbent, we are interacting with the economic modelers and the life cycle analysis teams to be able to understand the impact of that technology. And I get that we are at a early stage applied research stage. I don't know how that scales. We'll talk about scaling. Once you get closer to actual demonstration plants and more industry driven, I don't know how you develop a consortium, But there has been other consortiums in other industries where you can identify the pre-competitive issues that the industry is facing and work effectively to overcome that. So it's not a singular problem. It's more than just a really keen researcher being very creative in their laboratory. It's really about trying to assess that technology as it impacts not just the stages of the supply chain preceding and downstream, but to also bring in all of these other factors that we've been talking about from the ESG, the techno-economic, all of that I think is important in developing supply chains.
Thanks, Tom. Scott and then Simon.
I think one of the challenges, right, coordinating across scientific fields, institutions, organizations, administrations, right? And so I think one of the things that I see, having retraced the footsteps of people doing this work for the USGS in the 70s, is in terms of funding and support, right? Everyone's got their strength and what they can bring to the table. But how do you maintain, one, how do you coordinate, but two, how do you maintain it long term, right? It's like, yeah, sure, we can have some funding. It's like a fire in the walk when it's gone. And how do you maybe spread that out over 10 years and maintain a focus in terms of, a coordinated vision and what's actually making a difference? And to me, that's kind of the challenge. Things become a bit disjointed when it's like, well, I did this and someone did that. And the coordination, if there would be a way to establish more of a longer term view and commitment. I know we all want it yesterday, but I think we've demonstrated that's not going to happen.
Simon.
I think industry kind of downstream is pretty good at kind of consortium approaches. We've seen things in Nevada where, battery manufacturers and some exploration groups are getting together to work with the university and put in like NSF engines bids and so on. But I think one area we could maybe learn from is Australia, where, the Amira consortium model, but basically, a group organizes a consortium around a specific problem or a specific mineral deposit, in which case, what we have here is a whole load of lithium brines that we could actually benefit from learning a lot more about and learning how to process, but there's also a lot of commonalities here that something like a consortium approach could well work together. And I think there's things to learn from other areas where they have these sorts of approaches to solve exactly these sorts of problems. If anybody's not familiar with Amira, they basically coordinate groups of industry funders along with university researchers to work together to have projects that can often have multiple iterations. Like they've been working in mineral processing on a project version A, B, C, D, E since the 1960s and so on. So it's a really effective approach, but it also kind of gets over some of those confidentiality issues that others have mentioned here. If you get a group together to work on specific problems, you can overcome some of those issues.
That's really, really helpful. A couple more questions, and I think we're going to move on. This is a timely topic, witnessed by the number of people here and the number of folks who are online. Can you speak in an R&D context? Can you speak to the urgency of the R&D challenges? Do we just take our time? We figure this out in 10, 15 years. Is that pretty good, or is this, we have to get after it now? Sophie.
I don't think I have to remind anyone that extinction is forever. And so when it comes to thinking about the biological resources and the imperative to make sure that our actions protect them, we need to know what's there in order to be able to protect it. So there is some urgency in being able to define what species are present in particular locations, and to be able to have a plan to prevent for their extinction. So there is that. I think that is complicated by the challenge of our mining law as it applies to public lands. Whereas for other activities, we can do programmatic environmental impact statements, such as were done for renewable energy throughout the West. But for this activity, it becomes more difficult to do that type of assessment, that type of analysis, and look at things more broadly across a region. Yeah, I'll stop there.
I would say, given the trajectory of trying to decarbonize, all aspects of our economy and of our society, and especially in California with the timetable that's set there, this is really an urgent issue. The fact that we need these materials to do the decarbonization, to electrify our vehicles and to have battery storage. So there's the challenge is to do this right, I guess, and to not end up with these green energy sacrifice zones. So figuring out how we assess what the environmental and social risks are before we go forward, I think is really important. And so how do we come up with a template to do it right, I think is a key challenge.
Thanks, Pat. Simon, you had another one, and then I'll go to Scott.
Yeah, I think I just want to echo what Pat says and what Sophie mentioned. That this is the energy transition is essentially happening right now. We are going to see increased demand for all sorts of metals, and lithium is a key one of them. And unless we work out how we can actually extract lithium in an environmentally and socially acceptable manner, then we're going to end up in a situation where we've got an awful lot of development happening downstream, an awful lot of lithium demand, but we have no supply. And that means we're either beholden on insecure supply from elsewhere, or a whole load of manufacturing isn't going to happen. And that's going to have significant impacts for climate change, for the US economy, and more. So I think it is urgent. We need to not only do the R&D, we need to understand what the uncertainties around all of this are, just in case, what happens if a project succeeds, if a project fails, what the implications are on all of that, and how do we fit in the global sector as well. We're talking about domestic resources, which are crucial, but we're also part of a globalized economy, and we need to understand what other countries are doing as well.
Scott.
So basically what Pat and Simon said, I was going to say there's two prongs, right? There's the energy transition. That's urgent. But then there's the criticality issue, right? Which is, and the importance part of the critical is, what does it mean to our industry or our economy domestically? And I can tell you from working internationally in this issue for a long time and with many international colleagues, the EU and China both view this as an urgent issue. And so in a geopolitical context, you'd have to wonder if we're missing something if we don't consider it urgent.
Which actually tees up the last question, and then we'll finish up here. The question, there's a question here online. How does the U.S. centric R&D and brines and all the related topics, how does this compare to the comparable R&D or efforts that might be going on elsewhere in the world? Whether it's EU, China, other parts of South America, other parts of the world. Are we leading the pack? Are we sort of, where is the U.S. in terms of its R&D in this broad set of topics you all have mentioned? Yeah.
So I can speak, within my research realm, South America and the opportunities there that have been presented to work on projects. So my research team work that Scott is doing within the USGS and collaboratively with our international other academics, researchers in the industry. There's a lot of knowledge that's been gained there. Some other, and I'm just going to focus on closed basin brines because it's such an open, big question, but there's other places in the world that it's hard to know about because there's not a lot of public information. But, the United States, it has, now these emerging lithium brines, which are the low temperature geothermal and the high temperature geothermal. And there's a lot of opportunity there to expand what we already, sort of know about these places because of geothermal activity, oil and gas development, and that should really be capitalized on.
And Pat?
In Europe, there's quite a bit of activity looking at geothermal brines as a source of lithium. A number of startup companies, Vulcan and Lithium de France, are two such entities. There's EU funding for this work. BRGM, sort of the USGS of France, has been doing lithium research, and they just published an atlas on geothermal resources in Europe this past couple of months. So a lot of activity and a lot of potential for collaboration between researchers there and here in the US.
Thanks, Pat. Okay, we are going to move on. We're now going to have some closing presentations by basically the federal funding agencies about current or available or oncoming research opportunities. And the first speaker is Hikam Hajaris.
Good afternoon, everyone.
By the way, Hikam is the program manager with the Fossil Energy and Carbon Management Office at DOE. Okay.
Thank you very much. Wonderful, thank you. Good afternoon, everyone. My name is Hisham Hajaris, and I'm the program manager for the Water Management R&D program at the Department of Energy's Office of Fossil Energy and Carbon Management. It's a pleasure being with you all this afternoon, and I will give a brief overview of the program. Next slide, please. So all water-related R&D within the Office of Fossil Energy and Carbon Management is managed by our program, which is housed in the Advanced Remediation Technologies Division. Now, historically, water management was split across two programs across different offices within FECM. The first, it was primarily focused on water management for power systems, which shifted from power plant water research and active water management operations to remediating coal power waste. The other program was the Produced Water Management Program, which has become a significant focus for FECM. This program is primarily focused on the characterization, treatment, and management of water produced during oil and gas operations. And we're looking at produced water across the country, across different basins of varying salinities and chemical compositions. Now, both programs are under the singular water management R&D program. A common denominator across both of these programs is the focus on water recycling and beneficial reuse outside of oil and gas operations and outside of general energy management operations, especially when it comes to beneficial reuse of for industry, agriculture, specifically non-edible crops. And the other objective is the recovery of critical minerals, rare earths, and other beneficial resources from these waste streams. These not only have the benefit of furthering the technological state of the art for water treatment technologies, but also help lower the costs of water management and enable the beneficial reuse to take place. Next slide, please. And here's the geographical distribution of our program. Since 2018, we have funded projects across 23 states. As you can see, a lot of the projects are in the oil and gas and coal producing regions of our nation. Many of the projects that you see in the Southwest, especially in the Permian, are relatively recent, which shows the shift towards produced water management. Next slide, please. Now, I mentioned that we reorganized both programs into a single program, and as part of this, we decided to take advantage of the synergies and interoperability between various projects to develop a system to help facilitate future R&D as well as optimize existing R&D. We have 4 primary R&D areas. Some of these we've always had, such as the advanced stream processes and systems analyses, but others, such as AI and big data, as well as biological and chemical characterization, are relatively newcomers. And we took a platform development tool, so we're no longer focusing on just specific projects, but platforms, especially on the digital side, that can be built over time, especially when it comes to data, when it comes to decision-making tools. We have actually three major efforts on the data side. One of them is the National Energy, Water Treatment, and Speciation Database, NEWTS for short. I highly recommend looking this up online. You can upload data or access data. So we're in the process of not only collecting and curating data in partnership with other organizations, other agencies, but also generating synthetic data using advanced neural networks to help address data gaps. And the goal of this is to help feed in high quality data that any modeling that your typical modeling tools can use with relative ease. And we're also doing chemical and biological characterization. This includes collecting previous samples, samples from our own projects, and samples from partner institutions, which again we upload to the database. And overall, some of the programs we funded not only have the benefit for the original scope of work, but they also serve as a platform to support new ones as well. This helps us avoid reinventing the wheel and lowers the cost significantly for testing new technologies. For example, we've had the brine extraction, storage, and test site in North Dakota, which I will go into detail in the coming slides. This project was initially intended for carbon capture, storage, brines, but with the capital investment we put in, and with the fact that we could treat highly saline brines in excess of 200,000 milligrams per liter, we realized that we could use this as a test bed for different types of technologies from different types of waste streams. And so that was the case for BEST. And we were able to test different technologies beyond the original scope, including for produced water as well as power plants. And it also has the potential for critical mineral recovery as well. To date, on top of the original technologies for which the BEST site was intended for, we tested 4 additional pilot scale technologies, which I will also go into detail in the coming slides. But yes, overall, we're taking this platform approach, building off of existing research, and this is especially significant when it comes to data. Next slide, please. Now, as far as our different research priorities, we have a number of areas that we're looking at, as well as a number of mechanisms with which we pursue and support this research. Many of you have heard about the typical funding opportunity announcements, as well as SBIRs. We're active in those, and we also relatively recently launched this new initiative called the Produced Water Research Partnership, which allows us to work directly with universities on critical produced water management issues. The focus currently, and the projects are ongoing, has been on the beneficial reuse of produced water. And really, this ties in very well with produced water characterization and treatment. It's really, all of it is about understanding the known unknowns, the chemical and biological composition of the water. And this has implications beyond just treatment, but also the beneficial reuse, especially when it comes to toxicological and health impacts, as well as the critical mineral recovery potential. Essentially, understanding what's in the water allows us to not only adjust the treatment, but also adjust the overall management strategies beyond the oil and gas wells and power plants. And of course, there's critical mineral recovery, which is also very much tied in with produced water characterization and treatment. So far, we have 3 primary project tasks that we're focusing on: lowering the cost of zero liquid discharge and resource recovery, compiling full detailed aqueous speciation and mineral saturation indices of produced waters across the United States, as well as leveraging the DOE's produced water optimization framework for rare earth elements or critical minerals from produced water. And so, these go from supporting basic science to on-the-ground operations for operators, and everything in between. Next slide, please. And very recently, we've announced a partial award selection for FOA 2796 last December. The water research and development for oil and gas, produced water, and coal combustion residuals, wastewater associated with coal power plants. And these projects give you an idea of where we've been focusing. Topics are as diverse as desalinated produced water as an irrigation source for non-edible crops, as well as a source for ammonia mining and carbon sequestration. And we're also looking at not only the treated water, but also the reject brine streams. And there has been a company that won an award, PVT Clean Energy, which actually uses the reject brines, which has been a major disposal issue, to have it as a material for the development of ultra-rate composite manufacturing. So it's a very unique project. I believe one of the first of its kind to actually deal with the waste stream itself, and not just the actual treatment of the waters. And of course, we have the characterization efforts that make in situ characterization more feasible. Again, the goal is really improving our understanding of the known unknowns. And this goes into both the environmental impacts as well as the economic potential for those waste streams as far as critical minerals are. Next slide, please. I mentioned about the brine extraction and storage test site. So this test site has been a critical enabler for technology development and advancement and across different types of wastewaters and with different technologies. So as you can see to the right, we have quite a diverse array of technologies we've tested, all of which are plugged into an existing pre-treatment system. This BESS site was actually a commercial saltwater disposal well repurposed for carbon capture and storage. And after we completed the carbon capture storage project, we repurposed it for treating power plant effluent, which we shipped over, and then produced water, which we also ship over from across the country. We are currently testing waters there from the Permian, from the Eagle Ford, from the Bakken. And after treatment, we take the samples and then we do further chemical and biological characterization of those treated samples, and then upload the data to the NEWS database for the public to use. And we've tested everything from supercritical water desalination to zeolite dewatering. And this allows us to simulate produced water chemistry and salinity from diverse geologic basins across the U.S. For my last slide, we have, sorry, next slide, please. Yes, thank you. Could you click again? I think there is, yes, I think there are two more bullets. Thank you, perfect. So as I mentioned before, we've been focusing a lot on big data. This is a very recent tool we have developed. It complements the National Energy and Water Treatment Speciation database I mentioned earlier. It's called CODART, the Constituent Data Replacement Tool, and this helps complete composition data profiles for aqueous wastewater feedstocks. And this allows operators to develop treatment and recovery process models. And as you can see to the right, you can choose the different machine learning models based on your knowledge of the data. And this comes with a guide once it becomes public to advise on the best models to use based on the data. So, we have random forests, for example. We have multi-layer perceptron models, et cetera. And this tool can use the user's data alone or combine user data with other data sources. And we have another model, we have other model development specifically for synthetic data generation. And again, the intention of this is to provide that high quality data to enable some of the modeling efforts that were talked about in the previous panel. So I don't probably over time. This concludes my presentation. Be happy to take any questions. And of course, please feel free to, check out our tools. They're available for the public. And please feel free to reach out if you have any questions. Thank you very much.
Thanks very much, Aiken. We don't have time for questions right now. We need to move on to the next presentation, which will be Alex Priskachev. Alex is a program manager in the Department of Energy Geothermal Technologies office. Alex, you've got about 10 minutes. Thanks.
Unmute. Okay. Hi, everyone. Thanks, Doug, for that intro. As Doug mentioned, I'm Alex Priestachev. I'm with the Department of Energy Geothermal Technologies office. I'm an engineer and I oversee and help manage our critical materials portfolio. Next slide, please. I just wanted to go through a brief overview of our office for those that aren't familiar with it. We have 4 main focus research areas that we focus on. One being an enhanced geothermal system. So this is where we're looking at hot reservoirs that might not have fluid or active fractures or open fractures. And so we're drilling into those and potentially creating those fracture systems and using different types of fluid to extract heat from there. Our hydrothermal resources is where kind of traditional geothermal sits. We're looking at hot waters and steam that are coming up and we're producing power from those. This is where also our critical materials portfolio sits, looking at the co-production between geothermal energy and extraction of critical minerals from geothermal brines. And then we have our low temperature resources where we're looking at lower temperature fluids that we can use for direct use purposes or introducing those fluids or ground temperatures to geothermal heat pumps for heating and cooling purposes. And then we also have our data modeling analysis group. And so all of these research areas are looking to increase all geothermal energy deployment through R&D and demonstration of innovative technologies. Next slide, please. Thank you. And so when we look at areas where we can both produce geothermal power as well as economic amounts of critical materials, this is a rare ask. And so through the hydrothermal portfolio, we've funded and currently funding an opportunity that looks to locate these areas of geothermal potential or areas that are currently producing geothermal energy, like in the Salton Sea, Imperial Valley, California, or areas that aren't producing power currently, but have a huge critical material and lithium potential, like the Smackover Formation. Next slide, please. Again, for those that might not be familiar with what I'm talking about when I mentioned co-production, this is a little bit of a cartoon of what we're talking about. So as all of our presenters have mentioned today, geothermal brines may contain a long list of dissolved solids and minerals that are valuable resources and critical materials like lithium. And so what's happening in general, the geothermal brine is being pumped to the surface and it is being sent off to either power production, or we can extract that mineral and send it off to our direct mineral extraction processes that a few of our presenters have mentioned, and I'll go in a little bit more detail what that is. And we can extract that lithium or critical material directly from the brine, and then that spent brine is then sent back into our reservoir where it's reheated and minerals could be redissolved in that brine, and the process repeats itself. And then we can look to produce lithium chloride, battery grade, lithium hydroxide, and other uses for critical minerals. Next slide, please. And one of the presenters today, Pat Dobson, led the work at Lawrence Berkeley National Lab, along with his other project team members. One of the things that we've funded in recent past here is a lithium quantification report of the Salton Sea, where Pat and his team looked at quantifying the amount of lithium in the Salton Sea known geothermal resource area, understanding the mechanisms in which actually allows lithium to be in an abundant amount in geothermal brine, and understanding the potential environmental impacts, how the extraction of lithium from these brines would impact air quality, induce seismicity, and other factors to take into consideration in the area. And then also conducted a huge amount of community outreach to inform the community on not only geothermal power, but also how lithium extraction in the Salton Sea would happen, what are the outlooks on that, and really just trying to inform the community and arm them with information that they would need to better educate themselves on what's going on. The results of this report and this research are, as you can see here on the slide, were outstanding. Pat and his team discovered that there's the potential for more than 375 lithium equivalent of more than 375 million electric vehicle batteries, which exceeds all current electric vehicles on the road today in the United States. And accessing this resource would enable the U.S. to meet or exceed this global demand of lithium for decades to come. And then just sort of, what does that mean currently as we look to produce geothermal power with lithium? Currently, within the Salton Sea, there's about approximately 400 megawatts of geothermal electricity currently produced. But the entirety of the known geothermal resource area of the Salton Sea has the potential to produce somewhere almost 3,000 megawatts of power, which means it could produce 375 million EVs. Next slide, please. Oh, sorry, I want to mention one thing on going back to the slide. If you want more information on Pat's work there's the escholar.org website you can visit to see the report in its entirety. Thanks. Next slide. One of the current funding opportunities we have right now, we have ongoing work, is a joint funding opportunity with our partners at the Advanced Manufacturing and Material Technologies Office. This is a FOA. We have 2 topic areas, 2 projects under topic area 1, looking at demonstration scale of direct lithium extraction, and under topic area 2, we have, or I think it was about 8 projects looking at R&D on direct lithium extraction and direct mineral extraction technologies. And so the goal of this SOA is to enable environmental and social responsible manufacturing of battery-grade lithium hydroxide from geothermal brines, not only in the Salton Sea, I should mention, but across the United States. Diversify the supply of lithium hydroxide, validate these in demonstration facilities, as I mentioned in topic area 1, and in topic area 2, looking to mature direct lithium extraction technologies. So these projects have kicked off this year. Some are still being negotiated, but there should be some projects are making great progress already, and we should look for results on these projects somewhere in the year to come. Next slide, please. All right, this is an exciting opportunity we've just announced it. We have a critical materials lab call funding opportunity that we have open currently. Applications, as you can see there on the screen, are due May 31st, which is an extension to our original ask. So there's still plenty of time, I hope, for those interested in applying. Again, a lab call is for those working at national labs to apply as lead. And then we're encouraging our lab partners to look to industry, states, and other academia to partner with on this. And if you want more information, the website is there on the screen, or you can just visit the Geothermal Technology Office website for more information on that. But in general, the lab call, we have the goals for the lab call are to investigate ways to access and maximize the extraction of lithium and other critical materials from geothermal brines, and also looking to diversify the domestic supply of critical materials from geothermal and oil and gas reservoirs. So in this lab call, we have 3 topic areas. One is looking at Salton Sea geochemical and thermodynamic database development. So going back to the previous panel talking about figuring out the mechanisms in which lithium and other critical materials are present in brine. So we're looking to develop a database of geochemical and thermodynamic properties of typical Salton Sea and other geothermal reservoir rock to better understand those mechanisms. Our topic area 2 is looking at how we can increase access and maximize production of these geothermal brines in sometimes very hot, up to supercritical conditions. And so we are asking under that topic area for teams to identify baseline materials needed to successfully operate in those sometimes supercritical conditions. And then our topic area 3, we actually had 2 subtopic areas under this ask. So our first topic area, and overall this topic area, we're following the basic framework of what Pat and his team have accomplished at the Salton Sea. So topic area 3A, we're looking at characterization of lithium or other critical materials of the Smackover geothermal resource area. And then also subtopic area 3B, we're looking at characterization of lithium or other critical materials or minerals across the U.S., places like the Salt Lake, Alaska, including Alaska, Hawaii, other places that might have potential that's not currently being utilized, and including oil and gas basins. So I didn't mention here on the slide, but we are partnering with our friends at Fossil Energy and Carbon Management under this topic area. So we're very interested in the lithium potential in oil and gas basins, and as well as, again, with our folks at AMTO looking at additional geothermal resources. So again, applications are due May 31st. If you want more information, you can reach out to, go to the link there, and there's a email address. You can get more information or reach out.
Alex, thanks
next
very
slide,
much.
please. Oh, okay, great.
Yep, Alex, we need to move on.
No worries. Thank you.
Okay, and you'll have access to these slides to for further follow-up and to follow up with Alex on some of this. Okay, our final talk here is going to be by Dr. Hendrata Ali at NSF.
Hello, everyone. Thank you. So my name is Hendrata Ali. I am a program director with the Division of Earth Sciences. My primary program is the Hydrologic Sciences program. And so I will talk to you today about the opportunities and investment that are at NSF that are related to critical mineral resources from brines. So before I start, I think I would like to summarize a few of the things that I heard today that are of relevance to this topic and for some of the programs that I will talk to you about at NSF. So the first thing I noted was that lithium was the big topic today. And if we had time to go into some of the examples of funded projects, you'd see that lithium is also some of the critical mineral that is mostly proposed on recently, at least. Climate change trends are important for the sustainability and the recharge of brine formations. I heard that hydrologic controls and processes are important for lithium resources. There's a need for geophysical surveys, large scale, low and high temperature geochemistry are important to be considered, and environmental impact, and also the biological and economic factors are also important. So you would see when I talk to you about some of the opportunities that exist at NSF that you could actually identify all of these different areas that come into play. So can we go to the next slide, please? So the first thing is that although there are currently no programs at NSF that specifically are focused on research on this topic of critical minerals in brines, there are many opportunities that could be receptive to research proposals on this topic across NSF. And you have opportunities that exist for unsolicited projects or proposals that can be submitted directly to disciplinary programs, cross-cutting or interdisciplinary programs if the topic aligns with the solicitations of the programs. So you could find programs in the Directorate for Geosciences, in engineering, the new Directorate Technology, Innovation and Partnerships, and Directorate for Mathematical and Physical Sciences, but also social and economic and behavioral sciences at NSF. So for example, I think if we come to the Directorate for Geosciences, specifically in programs in marine geology and geophysics, petrology and geochemistry, geobiology and low temperature geochemistry, of course, hydrologic sciences, chemical oceanography. All these programs and many others would welcome proposals on this topic if it aligns with the program solicitation. In addition to unsolicited proposals, you could also submit proposals to that are responsive to special calls and that are themed around critical mineral research. So these could be either through dear colleague letters that have been released, or they could be through new programs with specific program solicitations. So next slide. So here, I want to talk about dear colleague letters, and you could use the QR code to access a couple of the dear colleague letters on there, and you could use the program number and go to the NSF website. I would have the code at the end where you could also search these programs. So the Build a Resilient Planet highlights some of the priority research areas in the Directorate for Geosciences. And one of these has a dear colleague letter on novel approaches to critical mineral research in the geosciences, which is a DCL that was released last year. And we've received and already awarded some awards on this case. If we had time at the end, maybe I would talk about some of the awarded projects. So this DCL calls for proposals to support research for the discovery, the characterization, extraction, and separation of critical minerals, which is, of course, important to the topic we're discussing today. Another dear colleague letter is the critical aspects of sustainability that spans several programs and divisions across directorates at NSF. And this DCL is for programs that seek to support basic research through a cross-disciplinary program to improve the sustainability of resources while maintaining or improving current products. So a couple of DCLs in this group would be the critical aspect of sustainability in innovation solutions to sustainable chemistry. And this is through the Directorate for Mathematical and Physical Sciences for research that aims to improve the understanding of processes, efficiencies, separation science, manufacturing processes at scale, and also the upcycling and recycling of materials and chemicals, including critical minerals. The second DCL related to the critical aspect of sustainability is the critical aspect of sustainability in innovative solutions to climate change from the Directorate for Geosciences. And this DCL is a call that is intended for action that encourages the submission of proposals to answer fundamental questions related to novel approaches and solutions to climate change. Potential for topics include innovation in technologies for desalination, developing and innovating for environmentally benign methods for the sustainable exploration, exploitation, utilization of critical minerals and geomaterials that are relevant to clean energy systems. So again, this kind of touches on some of the things that were discussed today, and maybe that the last panel was talking about in terms of what are some of the needs for research on this topic. Just add my notes. A third DCL that we can talk about is about innovative use of scientific collections. That is a multi-program in directorates across NSF, and the DCL encourages proposals that foster innovation and diverse use of collections and digital data for novel research education, and training. And it offers opportunities to explore the use of collections and digital data in several areas of geosciences, including critical minerals and sustainable research. So that's another DCL that you could look at. And then we have the Clean Energy Technology Research Advanced by Interdisciplinary Science and Engineering, and the Early Concept Grants for Exploratory Research, also known as RAISE and EAGERS. And the DCL aims to support scientists to develop potentially transformative convergent fundamental research proposals in clean energy technologies. And then we have the Sustainable Chemistry and Engineering Materials DCL. Next slide. In addition to DCLs, we have cross-cutting interdisciplinary programs and special solicitations, and you have a number of them on the screen. So you have the environmental convergence opportunities in chemical and bioengineering, environmental and transport systems called EcoSeabed. You have the convergence, growing convergence research, National Convergence Accelerator Program, which was launched with the TIP Directorate, Designing Materials to Revolutionize and Engineer Our Future, which is a multi-agency initiative. We also have an NSF DOE partnership, NSF Small Business Innovation Research, and Small Business Technology Transfer, and the Industry University Cooperative Research Centers programs. So all of these opportunities are receptive to proposals that touch on the topic of critical minerals research, and whether it is in brine or otherwise. Thank you.
Got it. Thanks. That's a lot of programs to be thinking about and considering. Thanks all. This has been a really good conversation, and I know it's going to continue amongst this community. Want to thank all the speakers who came from away to join us here, as well as everybody who signed on. We'll note that we had about 450 registrants overall, a couple hundred or over a couple hundred folks who were online, and a lot of who hung in there with us all the way through. So it's obviously a topic of much interest, obviously a topic we're going to address again. And there will be a recording of the event posted in the next couple of days. Quick reminder, please subscribe to the Beezer listserv if you have not already. And it's on the webpage. And please fill out the post-event questionnaire. That's always helpful. Have a great day. I'm going to turn over to Margot really quickly.
Thank you all for joining us.
Thanks very much.